Okay. Hello, everyone. We're going to start now. Welcome to today's symposium on rethinking computational approaches to the mind, fundamental challenges and future perspectives. Today, we're going to explore different computational approaches in the study of processes of the mind in both brains and machines. And we'll focus on challenges and ways to overcome those or to respond to those. I'm Nadine, and I'm organizing this together with Federico Micheli and Tomasz Korbak. A few notes on the schedule. So we will first hear from three speakers, Joseph Lézier, Romain Brett, and Gaël Varocco. We'll have a 30-minute break and then hear from Konrad Kording, Jessica Flack, and Melanie Mitchell. After a 15-minute break, we will have a panel discussion among the four of them, that is Konrad, Melanie, Jessica, and Gaël. The talks will be 20 to 25 minutes each, so with 5 to 10 minutes dedicated to questions from the audience. So anyone who wants to ask a question can do so in the Q&A, and the most upvoted questions will be asked. So when you ask a question, please make sure your question has not been asked already. Feel free to also use the chat to get into an exchange with other attendees, but ask questions directed to the speakers only in the Q&A. We also have a live stream on YouTube, but questions posted on YouTube will not be considered, only here on Zoom. And finally, please note that we also have a code of conduct, which you can read on the event website. So that's it as to the schedule. So we can start with our first speaker, Joseph Lézier, for whom it is already midnight. Hi, Joe. A short intro. He's currently an associate professor at the University of Sydney. His research focuses on studying the dynamics of information processing in biological and bio-inspired complex systems and networks. He's also the lead software developer of the Java Information Dynamics Toolbox and Information Dynamics Toolkit XL and Python for using information theory. So yeah, Joe, are you ready to share your screen? I'll just wait a second. I need to allow you to share the screen. So now you should be able to do that. Okay, looks good. Can you say something? I'm not sure I can hear you. I can't hear you, Joe. Mm-hmm.
How about now? Are we okay?
Yeah, it works now.
Can you hear me now, Nadine?
Yes.
Oh, okay, good.
Mm-hmm.
I can't hear you though, so something else has changed at my end.
Oh.
Let me see. Okay. So my audio, I'm on Linux, and sometimes it decides to switch all the audio settings on me.
I know this problem.
For no good reason. There we go. Now I've got you. All right, good. So okay, I can hear you and cool. You can hear me. Fantastic. Yes. Sorry about that. It no always worries. Does it at very inopportune times. Okay. So the first thing I'm going to do is to thank Nadine and the fellow organisers. I really am very honoured to have the invitation, especially to be on the bill with people whose work I've been looking up to for a long time. Before I get started, I'm just going to paste a couple of links into the chat that may be useful later on, including a link for slides from tonight if anyone's interested in following up on those. So let me start by saying, since this is a conference about the brain, let me start by saying that I'm not a neuroscientist. Now, if anyone's was listening properly to the introduction of me there, you'll know that's the case. And I say that out of love and respect to real neuroscientists. I'm a computers engineer who studies the way information is processed in complex systems in general. And the brain is one particular application area that I'm very fond of, but I still don't know that much about it, I feel. So I work with a lot of good people who do know a lot about it, and having that combination seems to work well. So the focus of my talk is going to be about the philosophy of how we think about information processing in complex systems, which I think fits well with what the organisers are trying to get at here. I'm going to talk about that philosophy through the nexus of the interaction between theory, enabling tools to put that into practice, and the applications that we've been looking at. And I think that interaction between those three is really key here. In order to make those applications to the brain work, as I say, I've had the good fortune to work with a lot of good collaborators, including in my own team, other collaborators in the University of Sydney and externally. We don't really have time to name check everyone, but I think it's important for me to acknowledge that, because as I say, I'm not a neuroscientist. So this is where what makes it work. So as I say, my research area is about what we mean by information processing in complex systems. So I'm going to spend most of the talk unpacking the philosophy behind that, and then thinking about how we can use the enabling tools to explore that quantitatively. So it's a tautology to say that the brain processes information. We talk about that a lot. As a complex systems person, I think about this in a wider context. So not just about the brain, but other complex systems, such as the way that schools of fish or flocks of birds process information. We can consider the way that the movement of one fish on the edge of a school in response to a predator triggers a neighboring fish to move away from the predator as well, which prompts another fish to move away and another fish, until we have this cascading wave of motion crossing the school, which we can consider as a cascading flow of information. That's called the Trafalgar effect, after a similar principle was used in the Battle of Trafalgar. We also talk about the way fireflies synchronize and the way that they process information in determining a synchronized state. We talk about the way they communicate intrinsically about the phases of their oscillation through their flashes. We talk about the way they make individual information processing decisions about whether to speed up or slow down their flashing rate. We talk about the way that they store information in their current phase, and so on. We talk about the way ants compute the most efficient routes to food sources. And we talk about the way that information is intrinsically processed in the dynamics of canonical complex systems like cellular automata, the way that blinkers seem to store information and the way that gliders seem to transfer information. So in thinking about how information is processed in complex systems, obviously we want to start by thinking about how computation is approached in computer science. Now, obviously, for anyone who's heard of Turing machines, that's the way we approach computation. Now, we don't have time to talk about exactly what a Turing machine does, but suffice to say, it's a very well-defined theoretical or abstract model with very well-defined inputs, outputs, an algorithm or task, and terminating conditions. The machine undertakes an instruction cycle that loops through reading and writing to tape, updating an internal state and moving where it's reading on a tape. In considering information processing or computation in complex systems, the key question, though, is, does knowing about Turing machines really help us to understand biological computation or computation in complex systems in general? And I'd say not really. We can take any of those examples we looked at in the previous slide and think about how it would help with those. We could take a flock, for example, and think, okay, well, we could, in principle, implement the flock on a Turing machine or a Turing machine to simulate the flock. We do that every time we simulate flocks in NetLogo, for example. Does that help us to understand information processing in that system? And I'd say not really. We need a new perspective. The problem is not that the brain or another complex system is not a Turing machine. That's kind of a side point. The problem is that Turing machine as a model doesn't really tell us anything useful about the information processing or computation that's taking place. So Melanie Mitchell, who will speak later, said that for complex systems then, the language of dynamical systems may be more useful to describe computation there than the language of computation itself. So we need a new perspective. And I think a nice way to think about this is in terms of intrinsic information processing as occurring whenever a system, say the brain, that starts from some initial states represented by different colors for different activities in different brain areas here, takes some inputs and undergoes a dynamical process that changes that initial state into some later state represented by a different activation pattern here and outputs. And this kind of view of information processing, which is, shall we say, not as restrictive as a view of computation, retains a focus on inputs to outputs and how they're mapped by some algorithm, but it doesn't shoehorn our perspective into a Turing machine straitjacket. There are differences indeed in what we might call information processing in this view and what computer scientists might describe as computation. There is no halt state here. There is not necessarily a goal or purpose to the information processing. And as I say, it's a very inclusive view. All of the examples of complex systems that I highlighted before could be seen as intrinsically processing information in the same way. So the question is, how can we make these notions more precise? It's one thing to start with that perspective. How do we actually make that useful? How do we measure how information is being processed? And the first step there is that we can acknowledge that the information processing taking place isn't just a mapping from inputs to outputs, but it's something that's happening in the distributed interactions that are within the system. It's something that's happening. It's something that's happening collectively in those interactions inside the system. So, as a start point, we can look at how computational information processing is talked about with regards to those interactions, and we see that we talk about how memory is used inside these systems. We talk about memory, for example, in the way that the fireflies store information in the current phase of their oscillations. We talk about signaling, the way that the fish, for example, intrinsically signal to other fish through their motion. And we talk about processing itself, the way that decisions are made to update states in both of those and all of the systems more generally. So with that said, what we want to do to try and put this on a more quantitative footing is to think about modeling computation via measuring information storage, information transfer, and information modification by basically quantifying those operations on information that are occurring in the distributed interactions inside the system. The goal of doing that is that we're trying to model intrinsic information processing in the language that's normally described in. And that should allow us to better understand the dynamics of neural information processing, for example, and its deficiencies. In other words, what we're trying to do is to model information processing in ways that can give us answers to meaningful questions that we might pose in neuroscience. So in order to start to quantify these operations on information, again, the obvious thing to do is to turn to information theory. That's where information is defined. Now, we don't really have time to go into all the fundamentals of information theory here, so I'm going to throw around some terms like entropy and mutual information. I've posted into the chat a link to some background video lectures that I have for a short course on information theory. So if you're interested in diving into some of that, that's somewhere that you might turn. In short, though, I like to say information is all about questions and answers. So we can define information as the amount by which a variable, a signal, a variable, be that an answer to a question, a signal, or a measurement of some sort, reduces our uncertainty or surprises us about another variable. Without going to it mathematically, I think that's a decent place to start. So we need to be able to quantify both uncertainty itself, which we use the Shannon entropy for, and uncertainty reduction, which we get from the mutual information. There are very well-known Venn diagrams that help to start us get our intuition here, but again, we'll kind of really have to skip over a lot of the background there. In those lectures that I referred to, I often use the game Guess Who as a really nice playground to think about these ideas. In Guess Who, you have to, each player picks one person, one identity that is them, that is their identity for the game, 1 out of 24 characters, and then they ask yes or no questions to the other person to try and narrow down who their partner is acting as in the game. And we can ask some really nice questions about how much information we get when we ask questions about that person's identity from it. For example, how much information do we get about the identity if we find out that the hair color of the other person is red? There's a whole pile of questions that we can ask there. In a neuroscience setting, we can ask all of the same questions in an analogous way. We could take, for example, a classic example where we have neural recordings from a face or house discrimination task, and we can map all of the same questions across and look at how we can use information theory to study, for example, the nature of neural codes, how the stimuli is encoded in the brain, or we can ask questions about functional relationships between the activity in different areas in the brain. So I think information theory is really useful for neural data analysis because it allows us to answer questions in neuroscience that are very naturally phrased, such as some of the ones that I've just posted up here. Not only that, allows us to answer these questions in a very much a model-free way that doesn't make assumptions about the system, that captures non-linearities. And there are a lot of different estimators for different data types. We've got estimators that work for discrete data. We've got estimators that work for spiking data, which is more of a point process. We've got estimators that work for continuous value data, such as fMRI or MEG measurements. So we can ask questions just like the ones I showed before about the nature of neural codes, but the kinds of questions I'm more interested in are about how we can model information processing dynamics. So to look at the dynamic interactions between the entities in the complex system rather than just asking about static relationships. And so to get at these types of questions, obviously we have to return then to our views on modeling information processing. So asking the question, we're returning to ask the question, how can we model the neural information processing dynamics? And we know, as I said before, we want to try and do this in terms of how information is stored and transferred within the system. We could, in principle, make a model of the information processing at the system level. But as I say, we really want to get at what's happening inside the system, in the distributed interactions inside the system, because we know that's where the real information processing is happening. So what do we mean by the interactions inside the system? Usually we're thinking about our complex system as a multivariate time series of states. We've got a whole series of variables, each of which we've got some kind of measurements of activity on. So this could be, for example, fMRI recordings, where each of our variables is a voxel in the brain, and the time series activity there is the bold activity on those voxels, or they could be beamform sources in MEG or so on. Regardless, what we're trying to do is we're trying to model how the next value in a target variable in the system, how the information is processed in determining that new value for the target variable. Where does that information come from? And so what we notice is that, well, that update, it's the output of a local computation at that point in the system. It has inputs from other source variables in the system. It has an output. There are rules or algorithms that determine it. And there's effectively a hold state once that output is generated. And it's not just one computation here or one information processing event. It's a whole series of coupled information processing events at all of the variables in the system. And so what we want to do is to model how information is stored and how it's transferred at each of these information processing events distributed across the system, and to use that to establish an information theoretic footprint for the dynamics that are taking place. The first stage that we'll look at in modeling information processing here is to model information storage in the system. And we do that by asking about how much information can we see in the past values of the variable that we're trying to model. How much information can we find there that is relevant to predicting the next value? And we'll use a mutual information to capture that. We call that the active information storage from the past that's useful in predicting that next value. Information storage in this way underpins periodic behavior, stability, the concept of memory, self-regularity, self-predictability. And these are all the kinds of questions that we can address using this measure. it's important to understand this is a model perspective. By capturing information storage in this way, it captures anything that may be physically stored within the variable there, but also information that might be stored in a distributed fashion to come out from the past of that variable into another variable and come back in later. Either way, we would model it as information storage in the dynamics of that variable. So it's a model perspective. The next stage in our modeling is to look at how much information flows through the dynamic interactions of other source variables with that target. And we use the transfer entropy to measure that. We ask how much information would we model as coming from a source that helps predict the next value of our target variable in the context of the past value of that target. If you're familiar with Granger causality, which is used in some areas in neuroscience and also a lot in economics, it's very much akin to that, especially when our variables exhibit linear relationships. The transfer entropy models a dynamic flow of information, not a static relationships as the mutual information would if we tried to relate the variables in that way. So that's really important. The dynamics here is really important when we're thinking about the updates on our target variables. It's important also to understand that it is a model view. It's complementary to the information storage that we would have modeled in our first step. The conditioning on the past here splits them out explicitly. But it's also a model view in that it's not measuring causality. Causality and this model of information transfer are explicitly two different things. And I think they're both useful for different reasons. Often people want causality, and that's fine. This is not going to do that. But on the other hand, the model view of information transfer also picks up things that causality does not. For example, highlighting emergent structures like gliders in cellular automata as dominant information transfer entities is not something that shows up when you look at measures of causality. Anyway, that's a separate issue, but I know causality is an interesting topic that's going to come up later, so I wanted to highlight that.
Joe, a kind reminder, you have 5 minutes left, roughly, so just as a reminder.
Yeah, thank you. So what can we say with that framework in place? How can we use it? And we've used it across all of these different systems. In particular, I wanted to return to the view that I think it's important that we're looking at this nexus between theory enabling tools and applications. And our work has covered all three of those in terms of theory, thinking about the fundamental framework that I've already talked through. With enabling tools, this is about connecting that theory to enable applications. And we've got two toolkits that allow us to measure these quantities in real-world data sets. JDT is the primary one. It's an information theoretic engine that we can use to measure these quantities on empirical data. And I'll give you a quick demonstration of that. The JDT toolkit comes with a GUI that allows us to pick an information theoretic measure we want to use, like the transfer entropy we've just talked about, to pick a data set, to pick an estimator, depending on the properties of that data set, and we can very quickly compute the information flow that we've seen between two of the variables in the data set and get code in Java, MATLAB, and Python to recreate that calculation and expand on it. So that's a really nice enabling tool, I think, for you to use that in your own work. We've put this into application in many ways ourselves, which I'll show you on the next couple of slides, as have a lot of other people in the field as well. In brief, I just wanted to summarize what kinds of things we can ask about neural systems with these measures. And there's three different categories I'd say we can use it for. We can look at how we can characterize different regimes of behavior in terms of how their information processing dynamics are different. We can look at how information processing dynamics change with respect to underlying neural conditions, for example, autism spectrum disorder. We can look at how the information processing dynamics change with respect to a different stimuli or task, or with respect to an underlying regime change, such as if we sweep through a critical phase transition between integrated and segregated behavior. The next category is looking at the space-time dynamics of information processing. So looking at highlighting information processing hotspots. for example, in an experiment where we ask someone to press a left or a right button, and looking at how information flows in different ways from motor control, from high-level control areas down to executing the left or the right button press. We can also look at validating conjectures about neural information processing, and that's something I'll mention on one of the last slides coming up. We can also look at functional and effective network modeling. This is something that's very natural to do with information flows. And our IDT Excel toolkit specifically is built for effective network modeling using information flow. I wasn't going to go into any of those examples in detail. The one that I did want to highlight was an example looking at exploring the conjectures made by predictive coding. I know one thing Nadine wanted to talk about later was how we can use some of these frameworks to try and get evidence for different theories about neural information processing. And that's one example here where predictive coding makes very specific conjectures about how information flows should flow up or down neural hierarchies. I don't really have time to go much into it, but we looked at a face house detection experiment where predictive coding would suggest that higher level face processing areas would transfer information about predictions to prime lower level face processing areas, and those lower level face processing areas should store that prediction. And using our measures, we found that we could validate at least some of those predictions, which was interesting. To finish off, I've talked mainly about the philosophy behind our views of modeling information processing in complex systems. We've talked about how this is set up very naturally to answer meaningful questions in a neuroscience setting. And we've talked about a categorization of what we can do in this setting between characterizing different regimes of behavior, characterizing space-time dynamics of information processing, and effective network inference as three of the main areas, but there's obviously a lot more things that you can do there as well. For example, using the toolkit that I've put the link in the chat there for. But let's take some questions, Nadine.
Yeah, thanks a lot, Joe, for your talk. Yes, we have one question from one of the organizers as well, from Tomek. So he's asking, can information dynamics measures such as transfer entropy help to understand artificial neural networks, for instance, large language models? Why don't we see machine learning interpretability research using these information theoretic approaches? Yeah.
That's a great question.
That's the question, yeah.
It's something that's it's something that we've sort of played around the edges of on and off for a while, and meant to go a bit more deeply into it, but haven't really done so. Some of the things that we've done have been, for example, looking at echo state networks and characterizing the different information processing capacities, let's say, in the reservoir, and looking at how that can be more or less helpful for different kinds of computation. We've looked also at some of the static measures of information, looking at some of the changes within a deep learning network as the network learns, looking at how some of the relationships between the neurons change through that development. There's a whole lot more that remains to be done. There's also some really nice work, I should say, from Paul Williams and Randy Beer a decade ago, looking at some of these information flows and how we can relate that to task. There's a lot of potential for it. It was Thomas that asked that. Thomas is absolutely spot on. There's a lot of potential, but no one's really done it yet.
Yeah, I'm also wondering, because information theoretic measures, they do apply for stochastic variables. I can imagine there are a few challenges related to that as well in artificial neural networks, because there we normally don't deal with those variables. So
you mean that there's deterministic?
Yeah, exactly.
Yeah, I mean that's not the fact that the system is deterministic is not a problem. We talk about a variable being a variable that we study being a stochastic variable, in that it's subject to some probability, but those probabilities don't have to be non-deterministic. For example, you can see in the background of one of these slides here, we're looking at that's an example of a cellular automata. I think that's elementary cellular automata, Rule 22. Some of our earliest applications were to cellular automata, which are deterministic systems. And there's certainly no problems at applying the measures there. We get really interesting results when we do, for example, highlighting that the glider structures or moving domain walls are the dominant information transfer entities there. There's no problem studying deterministic variables. I guess the problem might be if your variable was so deterministic that it only ever did one thing, then there's going to be, well, effectively no information in there. But once you start coupling those deterministic variables, then you get some variability, and the interactions can be quite interesting.
Okay, yeah, thanks. There is a second question. Maybe you can very quickly go into this, also to us posed by Tomek, but it's actually a question that I've been writing down for myself to ask to you today. So the question is a practical one. So about empirical estimation of information theoretic quantities. So when doing that, we often violate assumptions like Gaussianity, for instance, or ergodicity, or we resort to things like discretization or k-nearest neighbors methods, which do have their own problems. I feel, however, that we don't have a good idea of the magnitude of error when doing that. So when working with information theoretic measures myself, my impression is that what is actually lacking is a systematic study on estimating the magnitude of error to have an idea of how robust those measures are in empirical applications. So what would be your stance on that? Is that a research gap?
It's a great question. There's a lot of things I want to say, but we don't have time to say a lot of things. So I'll say some quick things.
You can say maybe something quickly, and then maybe you can write also something in response to that question in the chat. You're welcome to do that.
Sure. In short, what I'd say is one thing that we can do, we often look at a measure of statistical significance for our estimate. So we look at comparing our measure to a null distribution if we destroy the relationship between those variables. And that gives us some good insight into, whether we're measuring something reasonable or just noise. And it also gives us some insight into what the variability in our estimate might be. That's one thing. Another thing is that with the Gaussian model, if you're measuring a mutual information, it's actually a lower bound. So that's useful, even though you might be missing some of the nonlinear interactions there because of, I think that's what you're getting at about the assumptions being violated. It's a lower bound, so that's useful itself. I guess that's probably all we can say in terms of time.
Yeah. Let's keep it. Let's maybe stop at that point. But
sounds good.
Thanks a lot again for your talk.
That's okay. Thank you for having me.
Because it's very late for you.
Yes.
You can take a well-deserved break now. So thanks a lot, Joe.
No problems. I will drop off. I'll stay for a few minutes to ask and answer anything in the chat, but otherwise I'll drop off and go to bed.
Yeah, thanks a lot. Thank you. So the next talk will be by Romain Brett. So let me see. Yeah, Robin, you are there. That's great. So let me give a quick intro to you. So Romain Brett is a theoretical neuroscientist in Paris. Great, the screen sharing also works. And he has worked in cellular biophysics and systems neuroscience, specifically on modeling auditory perception, and who has done also a lot of reflection on the foundational concepts of neural modeling and computational neuroscience, such as neural codes, computation, and information. Okay, so when you are ready, the stage is yours, Romain.
Okay, thank you. Can you hear me well?
Yes.
Okay, perfect. Thanks. Thank you for the invitation and the introduction. So, so this talk is going to be I guess, a critical look at the idea of neural computation. So, as an introduction, I just want to say that I'm myself a computer scientist by training. I learned theoretical computer science, computability theory, complexity theory, Gödel's theorem, and etc. and so on. So it's with all of this in mind that I started my researched my PhD in computational neuroscience. And for a while, I used to say that I try to understand how the brain computes. It didn't come to my mind to ask whether the brain computes. And that's not a very scientific attitude, if you think about it. If the claim is not completely empty, then computation is a scientific theory of brain function. So what we should do is first clarify what this theory means, and then actually examine whether it's empirically correct. So what are we talking about? I'll start with a classical example of neural computation, which is navigation. So desert ants, for example, they can look for food. They wander around their nest, and then when they find food, they return to the nest in a straight line. And what's extraordinary about this behavior is that they don't use visual landmarks. It seems that, well, they must represent the position where they are, something like that. So let's say that the ant finds some food at some time, t, and then it would return to its nest in a straight line, so along a vector, which I'll call the homing vector, x. Now, suppose that actually it didn't find food at this time, but a later time, and then it comes back to the nest. So the homing vector would be another vector, but it's these two vectors are going to be related in a very simple way by the displacement of the ant. So that's the velocity vector times the time interval. And so because the behavior has this particular structure that the ant always goes to the nest in a straight line, you have a mapping which takes the homing vector at a given time and maps it to the homing vector at a later time. And it turns out that this mapping is a simple calculation based on two things that you can measure behaviorally, which are the homing vector and the velocity vector. And so now this mapping can be iterated from the nest to the final position. And what we get is a computational model of behavior with an input, which is the velocity vector as a function of time, and the output, which is the homing vector. And that computation we call path integration. So here you have an example of computational structure in behavior. But so far, I have talked only about behavior, it's just a description of behavior. I haven't talked about the brain yet. So the second step is to say that, well, the ant actually has a brain. And since it uses its brain to do that behavior, the brain must implement this computation. What does it mean to implement this computation? So the standard interpretation that you will find in many papers and books, philosophy in particular, is as follows. If we consider that the future behavior, so the actions of the animal, is determined by the state of the brain at a given instant, then there must be a mapping from the state of the brain at that moment to the homing vector. And so we say that the brain represents this vector x and also the velocity vector at any time. Now, two successive states must be related by the dynamics of the brain. And so what it means to say that the brain implements the computation is that the diagram commutes. That means that when the brain goes from one state to the next one, the variables that the state represents go through one step of the computation. So in this description, you recognize some familiar concepts of computational neuroscience, and in particular, the 3 levels of MAR. So you have the algorithmic level, the implementation level, and in between, you have representation which bridges the 2 levels. Now, this reasoning is pretty solid, but the main issue, as you will see, as I will discuss mainly, is what we call the neural state, what it is exactly. But before that, I first want to raise an important loophole in the reasoning. So it's an example which I took from philosopher Farid Zanoun. There's a completely different way to solve the path integration problem. It's not at all what the ant does, but it's something that you could do. You take a rope, you attach it to the nest, and then you take the rope with you. When you find food, you pull on the rope, and when it stands, you just follow up the rope to the nest. And you arrive to the nest in a straight line. So behaviorally, if you just look at the trajectories and so on, that's exactly the same as the ant. And that implies that everything that I've described in terms of behavior, this computational structure, is still there. But I don't solve the problem in the same way at all. So it would be an error, in fact, to call this a description of behavior. That's where the problem is. Because in reality, we are not exactly describing the actions of the animal, or of me, with the vector x, but the result of those actions in the environment as observed by us. So in the case of the ant, the homing vector actually corresponds to a particular motor command. But in the case of the rope, it does not. It actually corresponds to the direction of the rope. But the action that I'm doing is always the same. I'm pulling on the rope. So I'm not actually computing the homing vector. I'm solving the problem, but I'm not doing the calculation of this homing vector. So it's the results of my action that have a computational structure, but not my actions. And it follows that the rest of the reasoning collapses because in this case, the brain, my brain, does not in fact represent the homing vector x because that vector is in the environment and not in the actions of the organism. And so the brain does not in fact compute the homing vector. The way I solve the problem here is not by calculation. So more generally, not all problems that we solve are solved by calculation. Simply because all problems are not information processing problem. In this case with the rope, I don't treat the problem as an information processing problem, which is to map an input vector to an output vector. I don't do that. I just interact with the environment. So in some cases, behavior does not necessarily involve computation. So that's the whole point of embodiment theories. Now, of course, that's not what the ant does, because we know that if you move the ant to another place, then its homing vector direction will be unchanged. And that is what philosophers like to call representation-hungry behavior. So I'll assume that the behavior of the ant is actually of this kind, and it does have this computational structure. And now we'll move on to the question of neural states and so on. So recall the reasoning. If the brain state determines the actions of the organism, and if indeed the velocity and the homing vector are properties of the actions of the organism and they're not in the environment or in the interaction, then there must be a mapping from the brain state to those properties. And so that means that potentially you could read in the brain the position of the organism. That's correct, but we really haven't said much when we say that, because if brain state encodes all future behavior and action, then the same vector, the brain state, also represents lots of other things, like a shopping list that you have in mind, for example. Now, that is not at all a symbol in the sense of the computational view of mind or in the sense of a variable in an algorithm, because the variable in an algorithm stands for something in particular. So in the idea of a symbol, there is necessarily a form of reductionism. That is, that there's a subset of the brain that represents a variable. And that leads us to the standard idea of neural computation and neural representation, where it is a neuron or a group of neurons whose activity plays the role of a variable. And typically, the method in neuroscience is to exhibit a correlation between some property in the world and the activity of a neuron or a group of neurons. The problem with that is that typically the activity also varies with lots of other things, which are not necessarily tested in that experiment, such as other features of the stimulus or other stimuli or the context or what the animal is trying to do and so on. So in fact, in general, those activity that are identified in the brain do not have the quality of symbols, things that could be used in an algorithm. So all this is explained in more detail in my paper on coding, so I won't go in more details. And I really want to focus today on the notion of neural state, which is a critical point. So remember the key idea: the brain is a physical object. It's in a certain state, which characterizes that object, characterizes the brain at that moment, all you can ever know about the brain. And that state must predict the actions of the organism. So that implies that from the state of the brain, well, you can map it to the homing vector and other things. So that's the idea of a state. And of course, you have this idea in physics. For example, you take a ball, it has a state, which would be in mechanics, its position and speed. So that if you know the position and speed of the ball at this time, then you can predict the trajectory. And that is what a physical state is. It's a set of properties at a given moment that completely characterize the future behavior of the object or the way it might interact with other objects. A computational state is something like that too. But now comes the confusion, because what people typically call a neural state, practically in neuroscience, is not this kind of thing. So here's one example, but it's very typical. You count the number of spikes produced by a neuron between 300 and 1,000 milliseconds after the presentation of an image. And this count is then considered a representation. But this measurement is not at all a state in the sense that I discussed just before. And therefore, it cannot be in correspondence with a computational state. It's not a state, it's a temporally extended measurement of brain processes at a fixed time after the stimulus. And that's why we call it neural activity. It's some activity, it's not a state actually. It's a count of historical events that occurred during an experiment, not a state in the sense of a physical or physical state. So now when you try to fit this with the computation model, it doesn't work at all, because this is not a state, but a measurement, so it doesn't undergo dynamics actually. Properties of a process are abusively called a state so that they can be said to be updated by neural dynamics, but that's false. Properties of a process are not themselves updated by the very same processes. Neural activity is not a computational state. So the diagram is never going to commute. Now, the only way to make this work, you can make this work, is by having the iteration map the measurements of some neurons to some other neurons. And this is what is done in feed-forward networks, in deep neural networks, for example. But this trick doesn't apply to the brain. Neurons are coupled, and the output and input are also coupled through the body and the environment. So when I wrote my paper on the neural coding metaphor and the abuses in the neuroscience literature, perhaps the most common objection I got was that I was attacking a straw man. So when people say that a neuron encodes the orientation of edges, all they mean is that there is a correlation between a stimulus property and its activity and nothing more. People would say that they don't mean more than that, that it's causal or that it's state or things like that. Well, that's demonstrably false if you look at the literature, and that's what I tried to show in the paper. But what's interesting is that, on the other hand, philosophers of cognitive science, and I gave a few examples of representative papers, on the other hand, they seem to take those loose claims for established scientific facts. Neuroscientists really have established that there are neurons whose internal state correspond to some mental property. But apparently they're not aware that neuroscientists use words such as neural states and codes and representations with little care. So most philosophers agree that to implement a computation is something like this. That is, that transitions between neural states map to transitions of a formal algorithm. So you would see that in Chalmers, Putnam, Searle, and so on. But what they apparently don't know is that what neuroscientists call neural states are in fact not states at all. They're already properties of the processes. So they can't be again subject to brain processes such that would correspond to transitions in an algorithm. So to conclude, well, does the brain compute? Well, some aspects of behavior have a computational structure. So I give one example, and there are others. But not all behavior is computational. And neural dynamics, more generally, is not, well, it's not generically computational. So, and in particular, it's not obvious at all that perception is a computational process. It doesn't follow from any description of the dynamics of neurons. So thank you. I stop here and I'll take questions.
Okay, thanks a lot, Romain. We so far have no question in the Q&A, so anyone who wants to ask something can do so now. In the meantime, I do have a question, something I wanted to ask you. So I think, so one thing you generally criticize, I think, is that something like something we consider to be a psychological unit, something like the perception of a face, for instance, doesn't need to correspond to specific to certain neurophysiological states. So, for instance, to specific neurons or groups of neurons. So, my question is, what would be a general way forward? Is that a very hard problem to tackle? Do we need some, I don't know, some very new idea about how brain and cognitive processes relate to each other? Or is there some direction one could take to make a solution more likely?
Oh, yeah, thank you. It's a difficult question for which I don't really have an answer. So mainly what I wanted to do is to point out that this inference that we make implicitly well, has no logical basis, basically. Well, okay, there is one general comment that I can make, is that there's this tendency that we have, and I think many people, I guess, in philosophy have pointed this out, the tendency that we have to reify mental states. That is to say that, you know, a percept is some kind of thing in the brain. But a percept or a mental state is not a kind of thing in the brain. It's an activity of the brain. If your brain stops, you don't perceive. So it's not it's not actually some state, in fact. That's also one confusion that there is here, that is maybe due to language, really, that we use the concepts, or even the terms mental states. That is very misleading, as if it were a state as a physical state, like position and speed of a ball, for example. But a mental state is not that. It's state in the sense of a mood or disposition or something like that. But it's actually not the state of a physical object. It's more, like maybe an activity, something like that. So you're not going to find it either in the state of a neuron or even, I think, in the state of the brain, because it's not a state in the sense of the physical state. So we use this term, but it's very confusing, in fact.
So would a more dynamical approach generally be better to those kind of things?
I think a dynamical approach would be better, for sure, in general, when we, in general in biology, because biology is about processes in the brain and elsewhere. So even, I mean, in neuroscience, if you look at the models, and I mean by that the biophysical models of neurons, and those are dynamical systems. Physically, those are dynamical systems. Those are not computational systems. And on top of that, we try to make them congruent with computational systems, but that's secondary. and that is motivated by well, some computational structure that we may find in behavior sometimes. But it's secondary. If you look at the biological processes themselves, they are not computational processes primarily. They are dynamical systems. So yeah.
Okay.
Of course, to say that the brain is a dynamical system is kind of a triviality. So that's certainly not sufficient to address it.
Yeah, I understand. So it looks a bit like a hard problem really to tackle.
Yeah, but I mean, who said it was going to be easy?
Yeah. Okay, yeah, thanks a lot. I'm looking now at the questions posed in the Q&A. There are a few of them. So one upvoted question is, what do you think can be what do you think can be called as neural states? How can we measure them? Do you also think neural states actually represent anything other than themselves?
You mean what examples of neural states? Is that the question? Or
yeah, I'm not so sure I understand it myself. So
I mean, I can give an example of what we were saying. I mean, we know what it is. It's in actually you find them in the biophysical models. So for example, physical states would be a membrane potential, calcium concentration, this kind of things. These are states in the physical sense. What is not a state is the number of spikes in a given interval. That's actually a count of historical events associated to a system. That's not a state. So you have states, that you could take membrane potentials and so on. But
yeah, I think this is probably what the first part of the question meant. Then the second part was, do you also think neural states actually represent anything other than themselves?
Okay, yeah, that's a good question. That's a bit related, I think, to your question too. Is the so again, that's the idea of reification. The idea that when we say that we represent something like some image, for example, when we imagine, we represent to ourselves the face of someone, for example. Well, we say that there is a representation in the brain, but it's a word that we use, but it doesn't actually correspond to a thing in the brain. The image is not actually in the brain. What we mean by that is that we are in the activity of representing to ourselves the image. So if we're looking for a neural state that represent that image, we might be just fooling ourselves, because if what we're looking for is an activity, we're never going to find it in a state. So this comes from the confusion about what it means to represent. And actually, there's a paper from Farid Zanoun that I mentioned earlier on exactly this confusion, the reification of representation, that we take it as a thing where actually it's an activity. Mark Bighar has worked on that too. Representation is something that we do, not something that we look at. Okay.
Okay. Yeah. Another upvoted question from the audience is, someone is asking, if all behavior is not computational, would it be possible to mimic behavior artificially using pattern recognition of the brain activity? If so, to what extent would it be possible? I can read it again if.
Okay, I mean, yeah, I'm not entirely sure of the question, but I gave an example of a non-computational behavior with the rope. Okay, so there are two things here. You could very well imagine a robot who would pull on the rope and do exactly this behavior. The robot will have a computer inside it, and we probably use it to pull on its levers and so on. So you could reproduce the behavior, except this behavior would not involve actually calculating the homing vector. So there would be some computation involved, but not the computation of the trajectory, in fact. So that's one thing. And then there's the second thing, which is the relation between computation and simulation, or modeling and simulation. So if you take, well, dynamical systems in general, dynamical systems are not necessarily computational systems. Computational systems are certain kinds of dynamical systems. But you can simulate dynamical systems, though. You can simulate the Hodgkin-Huxley model. You can simulate all sorts of systems. But those are simulations. So the fact that, well, the brain is, well, the dynamics of the brain are not necessarily computational doesn't imply that you can't simulate it. That makes sense?
Yeah, so you would say that it is possible to mimic artificially.
I wouldn't go that far, because I don't know.
Okay, I see.
The lucid answer to this question is I don't know. Maybe it's possible, maybe not, but there are arguments that it's not possible, but I don't know. Okay, I'm agnostic on this. I need more thinking about that.
Yeah, I see.
I would say that if you can model that, okay, one partial answer to this question is that if you can model it as a dynamical system, like a conventional dynamical system, then you should be able to simulate that dynamical system and therefore to reproduce it. But the question then is whether the brain is or can be modeled accurately or in all its features by a conventional dynamical system, and that is might not be that obvious if we looked at the biological side of things. And I'm thinking specifically about how cell works and the fact that it's not clockwork work. So I'm not sure I can really answer this question. I would say that within the framework of dynamical systems, well, so the cybernetic framework, basically, that should be possible. But if we go beyond that, I don't know.
Okay, thanks a lot, Romain, for your talk.
Thank you.
That was great. So you can have a look at the remaining questions in the Q&A. Feel free to answer those.
Okay.
So thank you.
Thank you.
The next talk is by Gaël Baroucourt. So Gaël, you are there? Yes.
I am there indeed. Can you hear me?
Yes, we can hear you.
Very good. Romain, do you mind unsharing your screen?
Yes, exactly. Yeah.
I know sharing is caring. Thank you.
Okay, you should be able to share your screen, Gaël.
You should see my screen.
Yes, that looks good. Let me give a very brief introduction. So Gaël Baroucourt is the research director at the National Institute for Research in Digital Science and Technology, and a core contributor to scientific computing in Python, scikit-learn, nylearn, and DataCat, amongst others. And his research focuses on the use of machine learning in the public and mental health sector, and the potential in understanding cognition and brain activity. Okay, if you are ready, then you can start, Gaël.
Thank you very much, Nadine. So I take a different point of view, and my talk may be a bit different from the others. Really, what I'm interested in is how do we establish empirical evidence? How do we, go from observations, data to scientific findings? And the goal of this talk is to be slightly provocative and hopefully make people think about how we're using models to do something. And before I start, I want to stress that I've done a few different things in science. I actually started as a physicist. I worked on quantum physics. my PhD advisor just got the Nobel Prize a few weeks ago. I worked for quite a while after on using brain imaging for cognition, and really trying to work on the statistical inference that goes behind this, using tools such as machine learning. And I really try to collaborate as much as possible with cognitive neuroscience or psychology. These days, I've shifted a bit towards public health, and the questions I'm interested in is how can we inform policy, including in mental health. So this was a really interesting experience, a scientific experience for me, because I've started working on sciences where there are absolute quantities, sciences that are very well quantitative. And these days, I'm really more and more working on sciences where the subject matter is very qualitative. But there's a common trend in all this, is how does scientific knowledge or just knowledge actually emerge from data? And can we somewhat, control this process, maybe statistically? And one question I'd like to ask today is, what role do models play in this? And so I'll first start about evidence in cognitive neuroscience, and I'll describe a bit some view I developed about how empirical evidence is used in cognitive neuroscience, and then I'll do a small section on wider epistemology, claiming that models are overrated in the progress of science. I told you this would be slightly controversial. So let's talk about cognitive neuroscience, and really the classic way evidence is gathered in cognitive neuroscience, especially in brain imaging, where I work most, is that we probe mental processes by oppositions. So we carefully craft an experimental condition that recruits the mental process, and then we do an elementary psychological manipulation with another experimental condition that's close by, and where we understand basically the difference between those two conditions. And then we reason on the contrast between the two. And this contrast between the two could be statistics on brain images. It could be statistics, so typically imaging neural activity. But before this, it was pioneered by reasoning on differences in reaction times. So really, the framework I'm showing is a fairly general framework. Why do we do this? Because we're trying to isolate mental processes, and mental processes are ongoing in individuals' cognition all the time, and it's hard to isolate them. So behind this, there always is an assumed underlying cognitive model. The manipulations that we design, the way we interpret those manipulations are based on some form of cognitive model, which I'm not defining precisely right now. And it's the idea of the experimental paradigm. The reason we say we have an experimental paradigm is that the experiment is tied to a view of brain function. So the tasks and the stimuli that we use should recruit the right mental processes. That is an assumption by itself. The opposition that we use should cancel out what we're not interested in, which we conveniently call nuances. This is basically assuming most of the inferences we do in cognitive neurosciences when we confront empirical data. So the visual system, for instance, is a paradigmatic example where successive experiments throughout time have revealed specialized regions. So long time ago, Hubel and Wiesel did very specific manipulations that isolated functions of the primary visual cortex, telling us that basically it responded well, it detected well edges, and then people worked out their way, higher and higher up the chain of transformations, showing that areas would be tuned to more abstract forms even showing that some areas were tuned to faces. And each of those experiments are actually based on a specific position that is actually based on an underlying theory that decomposes the mental process here being scene understanding, visual scene understanding. And so, one question we could ask is there a car area? And we could run the experiment and we would get statistical results, and we would conclude that, well, some regions respond to cars. And now the problem is that we can run this way of running experiments with completely invalid ingredients. And with a very high likelihood, we would find brain differences. The reason why we would find brain differences is because experiments are imperfect, but it's an imperfection of the design. It's not an imperfection of the statistics. So we could do basically modern phrenology, and we could use this framework to try to validate phrenology. So that's the first problem. A second problem is that the kind of questions we would like to ask is, what mental processes are supported by given brain structures? The problem is that the empirical manipulation that we do actually implies the observed response. So we can do different experimental manipulations and see pretty much the same brain response, or one that is not easy to distinguish statistically. And so people have been claiming that a given brain structure is related to salience, executive control, pain, but the empirical evidence does not directly give this. It gives us the probability of the neural activity given the mental process. What we would really like is to conclude that a given neural activity implies a given mental process. Now that's hard for multiple reasons. It's hard first because it would be a high-dimensional statistical problem. We have many brain regions, we have many neurons. How do we go from this to some entity, some brain structure on which we can specifically give an association? Another difficulty is that it requires analyzing data on many mental processes, maybe all mental processes, and that ends up being practically very difficult. And ideally, what we would really like is a causal claim and not just those correlations. Okay, so one thing that some people, including us, have been doing over the last decade is to shift a bit the way we do the inferences and start predicting the task from the brain activity using machine learning. Now, the first benefit it gives is a fairly trivial one, is that machine learning is a form of high-dimensional statistics. It resolves the problem of the dimensionality, the fact that we have many neurons, but to do this, it must abandon the well-posed maximum likelihood framework of statistics. So our general inference or general conclusions that we would like to come up with requires data on many, maybe all mental processes. And so to carry forward this research agenda, you basically need to aggregate a lot of data together and basically generalize across many different tasks. And here there's a problem that is that you need basically some form of calibrated labeling of mental processes in all the tasks. And you need to basically describe the tasks beyond oppositions. And that's very hard, even with specialists. And I said we wanted causal claims, and I'll come back to this, but machine learning is also helping us here. Okay, so machine learning is helping us solving the problem that we call the problem of reverse inference. It's also helping us because we can use very complex models that come from artificial intelligence to do a task decomposition that is less reductionist. So let's consider human vision. For human vision, we can use computer vision models as a model for human vision. And then the idea is that the computer vision model is a powerful model of the image. It's a powerful model of the stimuli. So ideally, it has captured all, or at least most aspects of the natural stimuli that are important for visual scene understanding. And then we can use its internal representations to describe the stimuli and to map them to brain responses. So when we're doing this, we're not decomposing the stimuli to a very abstract and overly simple representation. So that's nice because it avoids choosing a few ingredients of a cognitive process to study it. And then it can generalize across different experimental paradigms. So we're no longer locked in an experimental paradigm, we can generalize. So the current state of evidence in cognitive neuroscience is mostly with a focus on significance rather than signal fit. And the problem with this is it leaves the door open to the wrong models, such as phrenology. So I think we need to move forwards towards considering signal fit. And currently, most people use well-posed statistical model, but they must be overly simple to be well-posed. And so they don't answer the question of interest. And part of the modeling is actually transforming the question of interest into this model. And that's where the validity, the control on the inference gets lost. So the benefit of moving towards machine learning or AI to actually do the inference is that it enables to model the actual situations with their whole complexity. Now, most people are not very satisfied with this because they want some form of understanding. And I claim, yes, this is true, but the answer cannot lie in simplistic mechanistic model, which cannot be confronted to data, which unfortunately is too often the case. So that leads me to my second point, which is to claim that models are overrated in science. So the dominant framework for statistical reasoning is to formulate a probabilistic model for mechanical hypotheses, and then fit this model in data and reason from model parameters. The problem is that this completely breaks down when we have the wrong modeling ingredient. And so I claim that we need to reason from model outputs, and I'll show you why. So let's first look a bit about the history of science. The typical view that we inherit on physics, math, chemistry is that these science work by building models from the right ingredients, from what we call the first principles. Our models are built from first principles. But as I'll show you, if we look in the past, this is actually not how the science progressed. They actually progressed by defining the relevant constructs from wrong models. And let's take the example of mechanics. If we go back to early scientists in Greece, they were thinking in terms of the natural motions of objects. There was no notion of force or acceleration, which are the basic principles of mechanics these days. And the way this moved forward was by observation of planetary motion, for instance, by Kepler. And Kepler was just searching for regularities in planets. He was searching for what he called harmonies. And he ended up with laws that are very phenomenological, relating the period square to the cube of the major diameter of the orbit. So, I mean, these are not based on mechanism. And later Newton introduced the modern laws of dynamics. And he was able to do this only because he also introduced differential calculus. And so he was able to have the notion of acceleration, which was necessary. You could not build the laws of mechanics without acceleration. And the reason why he convinced people that those laws were good ones is that he could unite observations of celestial and earthly motion. So he could unite what he would see on Earth with what he would see in the sky. So what does this teach us? Well, the early scientists were lacking the key ingredients. The science progressed by models that were in no way mechanistic. And the validity of the model that stuck was established by its ability to generalize across situations and not by its ingredients. Okay, so we can say that, this is no longer relevant. Modern physics knows its law, it doesn't need this. Well, if we look at the 19th century, people were observing that there were anomalies in the orbit of Mercury that were not explained by Newtonian physics. And so they invented an additional planet, Vulcan, and observed it to explain those anomalies. Now, Vulcan does not exist. These were incorrect observations, but they were needed because those anomalies were actually due to general relativity corrections. So this is the idea of what people call in philosophy of science theory-laden observations, is that if you have too strong theory, you'll basically use that theory as a framework to interpret your observation. And you fast forward to today, people are using machine learning, so basically purely statistical model, even in things such as particle physics, where particle physics is the most precise, the most exact science, natural science that we have. And the reason they're doing this is that, so the particle physics is very precise, but there are lots of uncontrolled noise in the experiments. And so to model the noise, they're using pure statistical models. So my claim really is that phenomenological data fits have been crucial to science. Basically, science uses false models as a mean for truer theory, and I stole this sentence from the philosopher William Wimsatt. And when we have a bias towards some simplistic mechanistic models, so very pure, simple mathematical theories, but that bias is not adapted to the messy world beyond pure physics, and actually beyond physics in very pure conditions. The bridges are not built via very simple mathematical theories. And finally, I claim that generalizations or prediction failures in general are what make or break scientific theories. So I'll fast forward a bit, but I want to talk a bit about what makes validity and reasoning of scientific models. And the first thing I want to stress, and I'll somewhat, fast forward through this, is that validity is much more than statistical validity. Validity is the idea of being able to generalize. Validity is the idea that your reasoning and your experiments are built on ingredients that we're going to call constructs that you understand and that you can measure well. One example is intelligence. This is difficult to measure well. It may or may not be a valid construct. And finally, the way in cognitive neuroscience we tend to reason a lot is by wanting that the entities that we do not observe have a strong validity. It's called realism in the philosophy of science. But is this a good way to build a science? I don't know. We can debate about the validity of intelligence, but in physics, we never debate about whether a center of gravity exists or not. That's not a question. It's just something that is useful to observe, to explain the observations. So the way we reason in statistics and in sciences in general is often by reasoning via the parameters of our models. So basically, we craft a probabilistic model of the data, and then we reason on this model. But we can also reason on the output of the model. And I claim we need more of that. I'm running out of time, so I'll just go quickly. One reason why we need to reason on the outputs of the model rather than the modeling ingredients is that even experts cannot choose the right models. And I'm claiming this empirically. There has been a set of experiments, one in cognitive brain imaging, where people have asked many different experts to analyze the same data, and not in an adversarial way, helping them. And then they've confronted the conclusions. And the problem is that there's so much variability in the way the models are built that the conclusions are all different. So if we reason on the output of the model rather than the ingredient of the model, we can compare the output of the model to the observed data, and then we can conclude on whether the model is reliable or not. And finally, the only strong evidence about whether a model is correct or not is whether it generalizes, to new data, whether it explains observations. And if we want to focus on the internals of our models, we're going to focus on cleaner and cleaner experiments. We're going to focus on experiments that have no variability. That's called focusing on internal validity. And that actually reduces the external validity of our models. So I claim that we can still do causal reasoning. And the reason is that the notion of causality is the notion of intervention. We have observational data. We don't have controlled observations, interventions. So for instance, people who are sick tend to go more to the hospital. So we cannot conclude on the causal effect of going to the hospital. But we can build a model that relates the health context of the individual before going to the hospital and the outcome. And we can fit this model, learn this model on individuals that went to the hospitals and did not go to the hospital. And this will be a purely machine learning model. It won't be a mechanistic model. But based on this, then we can infer the causal effect of going to the hospital. And that is related to a field that is developing a lot today, which is causal inference with machine learning. So I'll stop there. I'll just say that machine learning or AI, so powerful data fit, gives methods that allow us to do inferences with imperfect theory. And I believe that these methods are extremely important in the fields of cognitive science and biology, because I do not believe that simple models will actually explain the real world. Thank you.
Thank you, Gael. Thanks a lot for your talk. Let me have a look at the Q&A. There is one question, or a few questions actually. So one from Galen Wilkerson, if I pronounce this correctly. The question is, if we only reason empirically on the outputs and generalization of the model, but don't know what's going on inside the model, have we really gained any understanding, or haven't we exported understanding to our collection of black boxes? This poses a very modern question. It's almost sci-fi. Perhaps AI methods will have their own journals that we cannot understand.
So it's a question I often get, and the question is, what does understanding mean? And I believe understanding means, so it's an ill-defined concept, but understanding means reasoning on the situation in our brain. And in a sense, it's not a very satisfactory situation indeed to have a big black box that is able to tell us, the future looks like this. It's just like the weather forecast. We don't understand the simulation itself of the weather forecast. However, we can decompose it and understand some ingredients, which we can then use as, say, a sailor to reason on what's going to happen in the near future. So I believe, science will progress in two ways. It will progress in a quantitative way with models that are too complex to understand, and quantum physics is deemed as too complex to understand in general relativity too. And then we'll have simplified narratives. But the point being that those simplified narratives are not more valid than the complex model. They're actually less valid.
Okay, thanks. Another question, it's more of an, it relates to something you've been talking about at the beginning, to maximum likelihood framework. So the question is, would Gael mind expanding on the issue of abandoning a well-posed maximum likelihood framework that he introduced early on in his presentation, for those of us who might not be experts in machine learning?
So the well-posed maximum likelihood framework would be the standard statistical view. The standard statistical view basically describes the observed data with probability distributions and then fits them by saying, I'm going to find the data that maximizes the likelihood, so the probability of observed data. I'm going to find a model parameter that maximizes the likelihood, so the probability of observed data. And this is the dominant framework of statistics. Is that it has served us very well But when you start having models that are too complex, you don't have enough data to do this. The model is ill-posed in the sense that there are many different model parameters that can explain almost as well the same data. And that's a fundamental problem of statistics, and it's related to high-dimensional statistics. And machine learning, which I don't see as in opposition to statistics, by the way, I really see it as part of statistics, has basically abandoned this and said, you know, I don't care about this. I don't care about this. I will no longer have strong guarantees. I will not be able to conclude on some aspects of my model parameters. However, I will be able to explain well the outcomes.
Okay, thanks. One more question from Vince. The structure of a CNN, only feed-forward, is quite different from the architecture of biological visual processing. How can machine learning promise to reach a whole space of solutions?
That's a good question. So basically, the models that we use for if we're trying to confront brain signals to models of the corresponding task, the model of the corresponding task is probably not doing the same thing in the brain. It might or might not, because it's subject to the same constraints. So, but also it's probably imperfect. And CNNs, for instance, the standard, like the good old vision CNN, do not really have a way of propagating attention back, which the brain has. And so my claim is not, that, we have a CNN and we've sold the brain. That certainly is not my claim. My claim is that we need to use rich models of the stimuli and then to confront their internals to the brain. And we do need to reinvent how we do things. But the game is still going to go on. We're going to use not only richer models, but also richer data, because you need to be able to reveal specific phenomena. And CNNs are not the end of the story, of course.
Okay, yeah, great. So I guess now, we can transition to a break. Thanks a lot for your talk, Gael, and see you later on in the panel discussion. So we're going to have a 30-minute break now, and then continue with Conrad coding. So see you in 30 minutes. All right. Hello, everyone. Back to our symposium on rethinking computational approaches to the mind, fundamental challenges and future perspectives. We're going to continue with Konrad Carding. A few notes on the Q&A again. So if you want to ask questions, questions from the audience, then please do so in the Q&A. And the most upvoted questions will be asked. Check beforehand whether your question has already been asked. Use the chat to get into exchange with other attendees if you want to. But again, questions for the speakers, please do ask them directly in the Q&A. Okay, a few words on Konrad. So Konrad is a professor at the University of Pennsylvania. He trained as a student at the ETH Zurich, then worked at UCL in London, followed by MIT and the Northwestern University. His early research focused on computational neuroscience relative to movement. Then he's been discovering ways in which new data sources, as well as emerging data analysis, can enable new possibilities. The current focus is on causality in data science applications and in the brain, and how the brain does credit assignment. All right, Konrad, the stage is yours. If you want to share your screen. Great.
Wonderful. Thank you for having me. And thanks for everyone for being there. And I just also wanted to briefly mention how much thankful I'm for the organizers. I think it's really important to center these topics. Where are we going and why are we going there? So let me jump right in. Let's first talk about maybe the super simplistic way how a lot of people conceptualize neuroscience. I'm not endorsing this in any way, but a lot of people, at least in the background, have theories that are a little bit like that. How is neuroscience to progress? Well, we take brain and behaviors. We're ultimately interested in how these behaviors, how all that human thinking comes about. And we then kind of describe what the brain does in terms of what brain regions do. And then we describe what each of them do, maybe with respect to what their microcircuits in them do. And then we describe what each microcircuit does in terms of what the neurons do. And then we describe the neurons in terms of what the molecules do. And then we understand the brain. That's not how it's going to work, but that is kind of like a bit, or that's certainly how I feel a certain mainstream approach that the field has. And if we zoom into the logic of each of these pieces, they all boil down in a way to a causal question. Like, we want to know, how does a part of something make something happen at the bigger level? It ultimately boils down that we have the parts. They have interactions, and out of these interactions comes a solution to some problem. Maybe a brain region detects a face or something like that. What are the necessary criteria for that? Well, for this way of talking about brains, the pieces must be meaningfully independent. Like if the division of computation to say brain regions doesn't work cleanly, then that description is not going to be very rich. And similarly, there's and also, like, if we look at things like information flow, ultimately it's still a causal question. Like, we view information flow as kind of saying, we have stuff here and now it moves there. So there's an implied causality there. And it has certain assumptions, like all approaches. Now, the first one is that the relevant causal inference / discovery problems are actually solvable. And I will argue that they're not. Then there's a notion that they must be simple in a way. And I have frequently argued that they're not. And let's jump right in. So why are causal answers so hard? We have perturbative techniques now. We can put a magnet on Konrad's head and boom, and like lots of neurons locally activated. But it's a very low dimensional stimulation. And same thing with optogenetics. Now we put in light, we're going to have our opsin in a bunch of cells, but they're still low dimensional. It's like, yes, it's there or it's not there. So we are, if we have perturbative techniques that we now have, they are super low dimensional, but the space in which our thoughts unfold is high dimensional. So at some level, we have a mismatch between the perturbative techniques that we have and the kinds of questions that we ideally want to ask. And then if we look at the non-perturbative approaches, observational approaches, the areas where we do functional connectivity and so forth, we have what I will call hopeless confounding, and I'll try and convince you that this is really a thing, which is the brain has so many channels. We will record from thousands or maybe tens of thousands if we have top state-of-the-art techniques. We are still recording from a tiny part of the brain, and the problem of confounding is if we want to estimate observationally how things relate to one another, the existence of other variables makes that difficult. And lastly, even if we were not confounded, if we could record from all neurons in the brain, we would still be underpowered. I won't be talking about this today, but I'd be happy to share the back of the envelope calculations with anyone. So why is causality so hard? Well, the world would be great if there were only two things in the world. Unfortunately, there's always other things in the world. In the case of neuroscience, there's the part of the brain that I don't record from. In the place of cognitive science, there are the aspects of human thoughts and thought that we just don't formalize in the experiments that we have. So we're always confounded. And there's a continuum of confounding. There's cases like Atari, ImageNet, Go, Chess that arguably have no meaningful confounders. There's things like StarCraft where we have some. There's things like medicine where confounders are basically everywhere, and therefore medicine is much, much more careful than, say, neuroscience at dealing with confounders. And thanks, medicine, because if you weren't so careful about this, I wouldn't want you anywhere near my body. And then there's confounding in the brain, where we have arguably 10 to the 11 confounders. Every neuron is a confounder. And I want to tell you a little about the intuitions in that space, and I want to say that the slides you'll see are part of the NeuroMatch curriculum. We have a QR code there if you want to just look at that one part, which is exactly what deals with causality. So let's build a little intuition about causality. Let's set up the simplest possible causal system. We have a vector X that unfolds over time. What we do every time step, we multiply this vector X with the matrix, making our new vector. We add a little bit of noise to it, and we apply nonlinearity to make sure it doesn't blow up. Now, A is the ground truth causal connectivity. That is something that contains how each component of this vector influences each other. Aspect of that. We assume Gaussian noise, we initialize to 0, like all those standard things. And then we ask to which level is correlation similar to causation. And this is what you see here. So what you see on the top is the matrix. So I set the number to 6. Otherwise, it's exactly that simulation. I set there's 6 variables only. On the top of it, you see the matrix that we chose. We choose binary matrices because, well, maybe it's an approximation of how the brain is, but in any case, it's easy to visualize, it's easy to understand. And we can visualize it in 2 ways, either by a set of errors or alternatively as a matrix. As things get bigger, matrices are much more useful. What we see at the top is ground truth, how causality really is. And what you have below is the delay 1 set of correlations. Now, and why do we expect them to be similar? Well, if one neuron is active now and it has a strong connection to another neuron, then we expect that other neuron, based on the dynamics model that we have here, to be active at the next point of time. And therefore, we expect strong delay 1 correlations in that. And now, so what you see on the delay 1 correlation at the bottom looks very similar to the causal interactions. So the question is, well, okay, like maybe correlation is causation and everything that we've always been taught in statistics is just misleading. Well, it turns out that as soon as we go to big systems, so we have the very same dynamic system initialized the same way, all comparable, the true connectivity matrix left, the estimated delay 1 correlations on the right-hand side, they're totally different. Now, what happened here? As we make the system big, it effectively produces its own activities, its own rhythms. A lot of this stuff happens through other neurons, whereas if we have a small neurons, it's there. Now, this is why we are so misguided about thinking about causation. The kind of small systems that at least Conrad's little brain can simulate in its head. In those kind of small systems, correlation is usually, unless we maliciously design it, correlation is very similar to causation. So we have this gut feeling that correlation is causation. But then as we go to bigger systems, that relation totally breaks down. And that's, I think, why we consistently in neuroscience and basically all other aspects of like big system science confuse correlation with causation. In the systems that our minds unfold in, correlation is causation, but in the real world, causation isn't. So here you see how similar ground truth causality A is to correlation here. It is very similar, around N of 5, 6 that I showed you. It's very dissimilar as we go to 100. Guess what? It would be radically different if we went to 10 to the 11. Okay, so is that fixable? Now, like, where's that problem coming from? Well, the problem one comes from ignored confounders. We are looking, if you look at the correlation matrix, at only pairwises. So all other neurons apart from those two, or all other dimensions apart from the two, act as confounders. So we might be better if we build bigger models. So now we can build joint models where we say, well, what if we only observe a subpart of the neurons? And again, we are basically good if we more or less record all neurons or all dimensions that are there. And as soon as we observe 20% or so, we are already very bad. Now, guess what? The brain has 10 to the 11 neurons and we record from 1,000. So we are not in this left part of this graph. We are very, very, very far on the right side of this graph. And arguably the same thing is in cognitive science. Like, humans have remarkably rich inner lives, thankfully. And in that sense, we may come to the wrong causal models if we effectively assume that correlation is causation. Now, let's this problem of what happens if we have omitted variables, we can formalize very elegantly. We can write it down as what we do is we usually do regression. No, and like any more complicated methods, they're just basically regression plus X. So they're all very similar in a way to regression. We write out regression. This is the standard equation for regression. We can then say, well, if there's some variables that we record from and other variables that we don't record from, what happens? In this case, X are the variables that we do record from, where we want to know what the causal effects are. Z are the variables that we do not record from, that will introduce biases. Now, this introduces a bias that persists for regardless of how much data you get, and that has the same form from the regular coefficient. The fact that it has the same form means that this term, that bias from the unobserved components, contributes as much per dimension as the variables that we do observe. And now that, of course, then means that if we have radically more of the unobserved ones than observed ones, then that bias gets to be arbitrarily large, and no amount of recording for longer or more subject will fix this. Now, this was just to share with you why kind of the causal paradigm that I think a lot of us are looking for in a way doesn't work. To just like summarize that causal paradigm is, from observational data, we can't hope to get there, A, because we're hopelessly confounded. I didn't talk about it. Even if we were not confounded and could record from every neuron from the beginning of your life to right now, it's unclear if we could then identify what that function is that the neurons do. So there's different flavors of understanding. You know, like there's a flavor of understanding where I want to know some truth about it. And for a lot of people, that captures an important part. Others say we just want to predict it, yet others say we want to fix it. Some people say we want to simulate it. And then there's like a deeper, like we want to understand how it works. And I think every scientist sits here on a different level. And we wrote a paper recently about how people really have different motivations, and that's perfectly legitimate. Now, I want to specifically talk about this like broader understand how it works way a little bit, because there's a problem. So let's think about complexity. We play the tic-tac-toe game. Probably no one in this audience is beatable at tic-tac-toe because we all kind of have a pretty good theory of that. There's 255,000 distinct games, and guess what? Very few of you will realistically have played all 255,000 possible games. However, it can be compressed. The rules needed for unbeatable tic-tac-toe performance are simple. If you can win right now, win. If you can avoid losing next round, avoid losing next round. If in doubt, take the middle, and if still in doubt, take a corner. And you play the rules based on the first rule that basically applies to your current situation. So tic-tac-toe is super compressible. If we look at the game of Go, it's much less compressible. And in fact, there's like hundreds, potentially thousands of years of history of trying to compress Go. First with people trying to teach one another how to play Go. Now people write books. But guess what? You can go to Amazon, read all the books on Go, and you'll still be an absolutely mediocre player at Go. I mean, you'll be better than chance. Everything that these books contain is true about it, but it nowhere contains all the things that you'd want. So you could say, there's lots of dimensions that are real. For example, win if you can, don't lose if you can, that's still there. And then there's concepts like thickness. There are whole books written about thickness in Go, and thickness is real. Good Go players can apparently agree on Go. And there will be more and more things, and they're all true, they're all helpful, but they're all in a way, none of them gets us there. So the question is, when we talk about brain and the mind, can we hope that there is a compact, human understandable part that carries most of the variance? Or is it that regardless of how many aspects you've already described, the bulk of the variance is kind of in that heavy tail? There's still more things of thinking about human beings. And if this is the way it is, this is actually very frustrating because it allows us to write an unlimited number of replicatable nature papers about the brain or human nature. They're all true, they all replicate. And yet it never gets us really closer to understand not much closer to understand what's really going on. Now, what would it mean to understand a neural network? Well, you can say there's two ways of formulating a neural network. There's the PyTorch code, the code that makes the neural network, versus there's the weight dump. Here's all the weights, how every single neuron in my simulation affects every other neuron. Now, let's think a little bit about how much information about the world does an intelligence like that have. And there's different methods that we can use for that. There's empirically, we can ask, I give you a neural network that does the kinds of things that Conrad does, recognize objects and all that. How much can I compress it? And which gives me a little bit of an idea on how much information I need about that. And you can, and then there's complexity calculations, and then there's some back of the envelope calculations, a lot of ideas. Distillation, take a network that says trained on ImageNet, understand the real world. We try to compress it, and wonderful, we can compress it by a factor 10, maybe even a factor 100. So there's a lot of compression in there. It just turns out that afterwards, it's still so big that no human being could realistically ever understand it. Now you can say, not only that, but even if you could memorize maybe all the weights that my system has after compression, that still doesn't allow us to understand it. So we can go towards architectures that are more compressible, maybe soft decision trees, and all of a sudden our performance is really, really bad. Which means that probably there is no compact way of, say, expressing the kinds of things that Conrad knows about his world. We can also do back of the envelope calculations about humans. Now, how much information about your world do you soak up? Well, maybe 10 bits per second. You can challenge me on that. Maybe it's 1 bit. We're trying to get the order of magnitude right. Now, a year has pi times 10 to the 7 seconds, 30 years. So it's like order 10 to the 10 bits, which would be 10 to the 4 bucks. And I don't think these books will be exciting enough that you will want to read those 10 to the 4 bucks. You can now say, where does that information come from? Some of the information comes from our DNA. It's upper bounded by the 6 times 10 to the 9 nucleotides that we have. But of those nucleotides, most are non-nervous system. Of the nervous system, arguably much is non-computational, much is not compressed. So arguably what you learn from the world is much more than what you are given from your DNA. And just to give you a flavor of why there's so much uncompressible information in the world, Conrad has blue hair. That's perfectly arbitrary. It could be yellow, it could be green, but it happens to be blue. Now that you know that, if you want to recognize Conrad from very far, you're going to use it for some tasks, like recognize if your friend Conrad is walking over there. So if the brain's not compressible, then the question is, can we somehow separate it into principles about brains and just data? And the argument in a nutshell here is, I can make you understand the PyTorch code to make an artificial neural network. In fact, I teach a course that does that, and Neuromatch teaches a course. The resulting network out of that is impossible for humans to understand. So let's think about the analog of that in neuroscience. And let me make sure that this one point is really something everyone takes home here. What I say is we shouldn't study the mind. We should study the process that makes the mind. Because the mind that you have, that every person has, in a way, depends on the past, on where they come from. And it depends on the future that people imagine where they're going to. And therefore, the mind isn't even something that we can meaningfully study. And even if it was, it has a causal nature that we can't get. And even if we could get at the causal nature, it has a complexity that's not compressible enough to give us really compact models that are really rich for how people operate. I mean, look, I grant you that there's some aspects of the mind that we can absolutely study. I'm not denying the existence of psychology. Now, don't get me wrong here, but it won't produce complete models that in a way we can view as satisfactory for the whole thing. There will just always be very partial models. And of those, there might be an infinite number of truths that we can discover about the mind, that none of which kind of really gets us to seeing the whole thing. Now, if we take that idea that we should study the process that makes it instead of studying where it is at the end, you can say, well, what are ways to focus on? You can say we want to focus on the architecture, because the architecture gives us inductive biases about kind of the world that we are born with, that we need to efficiently learn in the world. We can learn about objective functions. What is it that maybe people optimize, if this is even the right way of thinking about it? And we can ask, well, should the brain follow a gradient? And even if it doesn't quite follow a gradient, maybe gradients are a good approximative system. What I'm saying is this approach of, instead of studying the mind, studying the process that makes the mind, it is an area of thinking that we haven't thought nearly as deeply as we have about, can we understand the mind as it is? And you can say maybe this optimizes if there's cost functions. One thing that I think is very important is that coming from computation, we can actually know certain things about it. You know, like whatever algorithm makes the mind needs to be an algorithm that is efficient enough to reach the minds that we have within the period of life and the certain amount of data that we have. So sample complexity actually matters greatly. And this is something that with some exceptions, I'm trying to paint a very broad picture here, but with some exceptions, we haven't thought much about what are the computational constraints here. You can also think about data and embodiment, and Tony Zader just put out a white paper with a lot of people on, including myself, about how embodiment is an important part of that, and the data, of course, matters. You know, like embodiment itself is part of the mechanism. It makes causality arguably possible. So if I'm not in a world, what does it mean for me to have causality to interfere with the world? Whereas if I'm in the world and I can do things, then in a way, the problem of causality is much more defined. It leads to somewhat of a recasting of the problem of intelligence, and you can say intelligence needs to be defined in relation to embodied cognition. Curricula are necessary. Now, if we talk about the data set, a certain sequence of ways that we learn is more effective than other sequences. We could put toddlers into quantum physics courses. It probably wouldn't be very effective. And a lot of other aspects of the data matter. Very briefly, we can also define learning with respect to the future instead of with the past. Classically in machine learning, we assume that there's a distribution and we take samples from that distribution, and we want to get at more samples from the same distribution. And people have relaxed that somewhat in things like multitask. The distribution of task is drawn from a fixed distribution, IID, and we will experience new tasks. So that just kicks it up level. But in reality, you can say we live in a world that dynamically changes. We live in tasks that dynamically change. So we want to track this dynamic change, and that leads us into a different set of ways of formulating that. Now, for that, and then of course, if we want to go down a direction, then we might want to focus on continual learning, causal learning, curiosity, constraints. And unfortunately, I will need to wrap up here. Just one reminder, the standard trivial model of standard neuroscience that I started sketching in the beginning is this bottom-up reductionist framework. We want to have a description where we go from molecules to spikes to populations to behavior at some level. This is only one of at least 3 different causal chains. Now, there is an evolutionary chain, causal chain where there's the ecological niche that in fact makes the specification of brains, and there's arguably something unique about the human causal, the human niche, namely that causality is incredibly useful in the world in which we live, probably much more than where any other animal lives. And then there's, of course, a causal chain for learning, where you can say the niche and some specifications that we genetically have produce the actual brains. And I think the near exclusive, or like the very strong focus on the fast causal chain might be at the detriment of fast making progress. So very briefly, take home message. I think we all agree that the PyTorch code to make an artificial neural network is easy for us to understand. The resulting network isn't. So I think we need to do the analog of the fast and focus on how the mind is made instead of how the mind is like. And I want to thank everyone for listening.
Yeah, thanks a lot, Conrad, for your talk. So we have one question that I can see in the Q&A. The question is there any research to train artificial models to perform high-dimensional perturbations? Oh, we can't hear you.
There is it's so funny that it still happens. There is a large emerging field in the area of artificial neural networks and generally machine learning, where people look at the way humans actually reason and start working on computational approaches that do those things. That falls into multiple subdomains, including people who try and get at observational causality and others who try to get at perturbative causality. There's even a meeting for the causal machine learning community. It's called CLEAR. And I highly recommend that area. But like, yes, this combination of how we can learn in worlds where we can perturb, I think is an emerging wonderful field that people should keep their mind on.
Sir, did I get it right? You made a distinction between perturbational and interventionist causality? Or did I misunderstand you?
Yeah, no, I'm sorry. Let me be clear on what I mean with causality. My definition of causality universally is the following. If A and B are events, and if changing A to A star would have changed the probability distribution of B, then I say that A has a causal influence on B. That is kind of the interventionist definition of causality. That's the only definition that I use. And I would go one step further and say that anyone who talks about, there is this big debate on people in philosophy meaning different things with causality, but I don't think this is actually quite true in the field. So anyone that I talk with, if they say, oh, I don't subscribe to that definition, I have a different definition of causality, and I then read their paper somewhere in the discussion section, almost invariably, they start making interventionist claims where they say, oh yeah, we did that functional connectivity stuff, and that suggests that area X is a mediator for something. Like as soon as you say mediator, you subscribe, at least implicitly, to an interventional definition of causality. So I don't think there's actually all that much disagreement about that.
All right. Another question from the Q&A. Could you develop a bit on the notion of compressibility of neural networks? Can one compress some complex dynamical system relative to some specific observable, for instance, firing frequency, to be able to compress it efficiently? I can read it again if that was too long.
Okay, so if the task is, which is in a setting that neuroscientists often use, we are wonderfully compressible. No? So if there's some neurons that I can say decode from very meaningfully, is this Conrad, or at least putatively, there's some neurons that have those properties. And the task is only to recognize Conrad or to not recognize anything, then this is probably a reasonably compressible aspect, because you can say most aspects of what the brain is about are totally out. Now, I think this is an illusion that comes from the way we do experiments. So if I only look at one thing, then yes, I will need a very small amount of information to describe it. But if I then ask for generalization, kind of say, okay, it can recognize Conrad, can it also recognize Nadine? Can it also like recognize other people? Can it do meaningful things during a dance performance? So as soon as we then open up the box, it's as soon as we allow more things, we find that things are more higher dimensional, harder to compress, harder to understand. They're no longer linear. They look linear. Things look linear if we're just within like a very, very small part of space. But as soon as we leave that, then we leave that non-linearity, that linearity behind. So I think the way we do experiments leads us to wrongly conclude that we have a deep understanding in cases where we don't.
Mm-hmm. Okay, I think for the sake of time, yeah, we need to stop at that point. There are a few other questions in the Q&A. You can have a look at them if you want. We would otherwise proceed with Jessica Flack. Hi. So let me say a few words about her. So Jessica Flack is a professor at the Santa Fe Institute. She's also the director of the Collective Computation Group. She did her PhD in 2003, received it from Emory, studying cognitive science, animal behavior, and evolutionary theory. Her research focuses on collective computation and its role in the emergence of robust structure and function in nature and society. And I see you have already shared your screen. Yeah, if you're ready, then you can just go ahead.
Okay, can everyone hear me?
Yes.
Perfect. So first of all, thank you so much to the organizers. I think you guys have done a great job of getting really interesting questions on the table. So I'm really pleased to be here today. And secondly, say that I'm a bit sick, much better than I was yesterday, but I'm a bit congested. So please just bear with me. Okay, so what I'm going to do today is really go over 4 concepts that my collaborators and I have been developing, trying to formalize in biological systems to understand computation. I've got them here on the title slide: coarse graining, collective computation, hourglass emergence, and channel switching. So the talk is really just an overview of these 4 concepts, a very coarse overview. Now here on the title slide, we have a composite image of the physicist John Wheeler, and he's, as you probably know, inventor of the phrase "it from bit." And in the slide, he's at a Princeton blackboard and he's discussing what in nature can be quantized, but as if you were looking at, I made this image, as if you were looking at Walton Ford's, a painting called Falling Bow. And I love that painting because it's a really fantastic depiction of collective behavior. And both Wheeler and the flock are overlaid on a circuit. So the composite image captures the central theme of today's talk, which is how the components of biological systems coarse grain, and that is how they estimate the state of the environment collectively, and how these coarse grainings, when they're combined, collectively compute a solution, a phenotype, or an output, if you like, that is appropriate, hopefully, given the state of the environment. And what I've just said essentially summarizes what to me computation in nature is fundamentally about: converting information in the environment to work, largely by way of producing ordered states, by way of entropy production and minimization. Now, it's worth acknowledging at the start of the talk some of my positions and biases or assumptions. So the first is that the frameworks that we have for computation in biology and computer science are, in some sense, the ones we have at present are in some sense either system dependent, so the result of working entirely in neuroscience or molecular biology, or they are mechanism agnostic, and that largely applies to the computer science frameworks. Another assumption I make is that to discover the foundations of computation, which is fundamentally what I'm interested in, we need to approach the problem of computation not just from the mathematical and theoretical computer science perspectives, but also inductively, and that's really what the talks you're going to see today in the talk, by studying how a variety of systems convert information in the environment to work. Now, what these assumptions suggest to you is that I'm what might be called a computational Platonist. So I believe the foundations of computation are to be discovered, not invented. And along these lines, I subscribe to the idea that to build a theory of computation for biological systems and social systems, a formal language for computation needs to take seriously a couple of things: biological mechanism, information processing principles, the universal collective property of biological systems, and thermodynamic constraints. I won't say really anything about the last today, but the others I'll touch on a bit. So in this talk, I'm going to provide a kind of first motivation, a really big picture motivation for the approach my collaborators and I have been developing. And then I'm going to give a course overview of what we think the elements and architecture of biological computation are, for a variety of different systems, given our admittedly, and I mean this both in terms of my collaborators and I and everyone, the community, rudimentary understanding of information processing principles. And finally, I'll return to my computational Platonism point. So returning to Wheeler, now you can see more clearly the background in this photograph. And as I said, he's lecturing at a symposium for his 60th birthday at Princeton. And according to a Kip Thorne obituary that was published about him when he died, the drawing depicts an explorer's quest to conquer the great unsolved problems in gravitational physics. And I'm starting with Wheeler because he proposed in the paper that I've got on the slide, titled Information Physics, Quantum, the Search for Links, which is a paper, by the way, that he first presented at a Santa Fe Institute meeting back in 1989 before he'd written the paper. It was a talk. And he wrote in that paper, all things physical are information theoretic in origin, and this is a participatory universe. Observer participancy gives rise to information. He went on to write, it from bit, otherwise put, every it, every particle, every field of force, even the space-time continuum itself derives its function, its meaning, its very existence entirely, even if in some context indirectly, from the apparatus elicited answers to yes or no questions, binary choices. And later in the paper, he poses a central question, and I'd say it's a question that's sort of at the core of my research interests. It's the question of collective computation, really. How does the vision of one world, or at least an overlapping vision of one world, arise out of the information gathering activities of many observer participants? So he was, he's working in physics on quantum stuff, but he's really doing collective intelligence. So implicit in this question is the idea that the macro scale arises from interactions at the microscale, and going further to understand the macro scale, we need to go down to the microscale. Now, Conrad talked a lot about this, and in the collective behavior world, as well as in neuroscience and in many other areas of biology, this view is often treated with suspicion. Let me just go over some of the disagreements. So there's disagreement about how far down we need to go to predict and explain at the macro scale, a lot of disagreement. And I want to suggest that this disagreement stems from variation across systems in the degree to which collectivity or screening off of macro from micro is a property of those systems, and a failure of the community to recognize that there's this diversity. So I'm saying there's actually variation across biological systems in how screened off the macro scale is. And when it's screened off, we can predict and explain at the macro scale. And when it's not, we have to go down to the micro. So I'm going to sort of provide a framework today for starting to think about how we can ask that question to know whether we're doing the right thing in our work. Now, I want to say too, that I think the burden is on all of us as a community that even if we feel that our macro scale stuff is screened off, that we have to show that the variables we're focusing on at the macro scale are are not nominal, the result of observer bias, but actually fundamental, that they can be derived from the microscale, even if we don't need to do that in our work to predict and explain. All right. So that is a kind of very physicsy point, and I'm a strong advocate of it, and I will argue it. It's the responsible thing to do, is show that they can be derived even if we don't need them. Okay. I want to finally make this point, that you'll see a distinction that's going to come up a lot in this talk is between energetically constrained systems and systems that have a lot of information processing additionally. And I want to suggest now at the start, just to sort of prime you to this issue, that in systems that are heavy on information processing, we have to be particularly careful about these issues. And that's because there's error, and the system's point of view in those systems is particularly important. So we have to sort of really understand the micro-macro relationship and not assume we understand it in those systems, because it's going to involve observer dependency. Now, this debate's become more heated. This debate about how far down to go has become more heated in recent years because we have increasingly so much micro-scale data. And Asif and John Krakauer and David Popple and others discussed this in a very sort of like widely circulated paper a couple of years ago, which I recommend you guys take a look at if you haven't. I think probably most people in this group have. So in that paper, they sort of address this question about all this data and, what do we do with it and what's right to use, and the impact of technology on measurement and so forth. But another question is, how much of these data does nature actually use? Okay, how much of these data does nature use to make its estimates? Do biological systems use to make its estimates of its effective theories of how the world works? And as significantly, how does nature compress? Right? Not how do we as physicists and biologists do optimal compression given the data we have, but how does nature do it? So those are my questions. And I have this paragraph from Laughlin and Pines and others, Middle Way paper, which again, probably everybody knows, and I recommend you read it if you haven't. It's very interesting. I have this paper up here because I want to understand, are there essentially what they call macroscopic protectorates for biological systems? And let me just read you a little bit of this quote. So we say that superfluidity, ferromagnetism, and metallic conduction, hydrodynamics, and so forth are protected properties of matter. That means they're generic behavior that is reliably the same in one system to the next, regardless of the details. There are more sophisticated ways of articulating this idea, such as stable point renormalization group, but all boil down to descriptions of behavior that emerge spontaneously. Not all of this applies necessarily to biological systems, but I think the basic idea is interesting and does. And is stable against small perturbations of the underlying equations of motion. Now, let's see, let me skip down a bit. Okay, more is clearly different, but we can ask, is plenty nearly enough? One could debate whether the existence of protected behavior on the macroscopic level is fundamental truth because of quantum mechanics or historical accident. And I would add to that, or because of the way components process information, errors and so forth. That's a little different from history. So do we have the tools to discover protectorates? The fact that length scales between atoms and small molecules on the one hand and macroscopic matter on the other is regular, which we cannot presently see and about which we therefore know very little. This state of affairs would not be of much concern if there was a desert of physical phenomena between the very large and the very small. But as we all know, there is life in the desert. Okay, so again, it's the micro-macro relationship. And this slight frame shift is key to all I do in the stance I'm going to take in this workshop, which is that to make progress in the emergence and adaptive systems, we really need to start thinking from the system's point of view. And implicit in this question is several provisional information processing principles. First, at any time there's a perceiver, a la Wheeler, to do uncertainty reduction, to get information, to do uncertainty reduction, there has to be processing or computation. And two, that information processing in biology is noisy and error prone, meaning that the path to entropy minimization and ordered state is not necessarily monotonic. These are not optimality principles in a strict sense, but they're more like empirical or pragmatic principles. And I say that to distinguish, it's not just history dependence. I want to really emphasize that. So this all comes from, I think, the fact that the universe is participatory and that entropy is increasing, right? So we need that entropy minimization. So now to further motivate this frame shift I'm advocating, I want to consider the following, which is that, oops, I think I'm missing a slide, which is that physics, physics is dominated by concepts like pressure, temperature, and entropy. And these emerge through simple collective effects and provide deep insights into the organization of the physical universe, the behavior. Biology, on the other hand, and that includes society and ecology, makes use of comparable collective concepts, including metabolism, conflict management, robustness, but of course, in contrast to physics, these are functional properties. Now, in physical systems, orders produce the minimization of energy. Adaptive systems produce order through the minimization of energy and via, in many cases, information processing. It's not unique to biology, it happens in physics too, but in physical systems too, but it seems to be playing a much larger role in biology. So why information processing is so central in adaptive systems, and whether it makes them fundamentally subjective and uncharacterizable by laws, unamenable to prediction, these are big open questions that at SFI we work on, and of course other places as well. Now, in trying to understand these questions, the relationship between micro and macro and how to predict the macro scale, the history of physics is informative. We don't want to mimic it, as you'll see, my talks about how we're not going to mimic it, but it's informative. In fact, I would say that much of the confusion that we suffer now was actually also suffered in physics. So what I've got here is a slide that sort of just sums up this very crudely, this microscopic, macroscopic relationship in physics. And I want to make a couple of points, which is that in the physics history of the relationship between thermodynamics and statistical mechanics, there are sort of three questions that come to the fore. The first is, do we observe predictable relationships among macroscopic variables? That's the first question that has to be asked. Like, you know, are there statistical regularities at the macro scale? Are these macroscopic variables fundamental? This comes back to my nominal point at the beginning of the talk. Can they be derived from the micro? If not, they're observer bias. But if they can, then we're in a position to start to say that the relationship among the macroscopic variables are law-like. And we can start to describe the macroscopic state of the system. And ideal gas law is one example. And I recommend you read Hasak Chang's, he's a philosopher physicist at Cambridge, book, Inventing Temperature, which gives a really great sense of the complexity and confusion of this debate around temperature in physics, macroscopic variable. I'll point out to you that, you know, this debate been playing out in collective behavior, neuroscience, and social evolution. You may remember in the early 2000s, there's a paper published by Karina Tarnita, Martin Novak, and E.O. Wilson. And the main paper was sort of on kin selection, and there's a 130-person response to it. Forgetting the main paper and just focusing on the appendix, which is really nice, Tarnita and Martin were really making the point in the appendix that kin selection equation, which is very phenomenological, the variables in they're nominal. They're not derived from first principles. And they spent the appendix showing how they could be derived from population structure, more or less. And so I recommend you take a look at that. And it's still something that we fight about. It seems kind of obvious to me, but it's not necessarily obvious to the community. Okay, so what I want to do now is give an example of how this micro-macro relationship has been worked out in a couple of examples in biology, done well, essentially. And so what I have in mind is the work on scaling by Jeffrey West and Jim Brown and Brian Enquist, Luis Betancourt, Chris Kempis, Van Savage, and many others, all of whom are my colleagues. And they're showing the example I'm going to put on the table now serves two purposes. First, it illustrates that deriving macro from micro in biology can be done, the practice of it, so to speak. But it's also going to illustrate one reason why understanding micro, how information processing changes our understanding of scaling and law-like regularities. So what we've got here are two slides showing the elephant slide is mass and metabolic rate, showing how they scale. And there's sublinear scaling in the case of mass and metabolic rate, which is a very, very energetically dominated system. And there's an economy of scale. So the scaling sublinear. The theory is well developed. They derived the scaling relationship, Kleiber's law, which is around for a long, long time before they did their work, from first principles. That's really their contribution. They understand the micro-macro relationship now, I would say, for the most part. There's still some things to fight about, but a lot of progress has been made there. Now, on the other slide, we've got scaling for social systems. And the one example I've got up there is city size, and I think it's like patent generation, crime, income, and so forth. And the main point there is the statistical regularity at the macro scale is superlinear scaling, so increasing returns to scale. But the relationship is not derived from the micro yet. They're doing that work now, and it's very hard, partly because the data have only started coming in much more recently than in the metabolic case. But it's also perhaps more difficult because these systems have more information processing and collective effects. That's my that's my strong view on one of the reasons why this is so challenging. And I really want to emphasize that difference. So when you get information processing and collective effects, it looks like the scaling shifts from sublinear in the energy dominated cases to superlinear, increasing returns to scale. Okay, so why is this important? Well, I think what's going on in addition to these collective effects, right, is that there's error and heterogeneous decision-making in these systems. So it brings us back, there's partly aligned interests, different windows on the world, components are at different developmental stages. So that heterogeneity is sort of captured here in this slide, which you can read, they're out of equilibrium, components are turning over, but the system's sort of staying more or less the same to some extent. There's a kind of effective equilibrium state derived from having multiple overlapping time scales and space scales. And you might look at this kind of thing and wonder about what I've been saying. You might think, well, given all this variability, it's amazing that there's ordered states at all. However, noise sometimes plays an organizing role. We all know that. And as I said, maybe one way these systems are achieving regularities by building multiple time and space scales, and those are essentially creating effective equilibrium states. So if we back out a little bit, what I'm suggesting is that components are collectively computing their macroscopic worlds in these information processing systems. They're creating hierarchy of time and space scales and using the slower scales, time scales, as a background, uncertainty minimization, prediction essentially. But to understand where these time and space scales come from, how they arise, we need to take into account that system's point of view. Now, this is sort of captured by the writer and painter Leonora Carrington, who, and I can't stand these little Zoom boxes that overlap on my quotes. She wrote, "To possess a telescope without its other essential half, the microscope, seems to me a symbol of the darkest incomprehension." Basically, we need to, peer into the telescope and the microscope in order to really understand what's going on. I just think that's just such a nice quote, given the points I'm trying to make. So to reiterate that a little bit more, consider the fact that life is hierarchically organized. As we know, the human body, for example, has 38 trillion bacterial cells, 30 trillion self cells, 86 billion of these are neural cells, or 100 billion now. There's 8.6 million people in New York City. There's just this incredible hierarchy. And the lower scales, which we often assume to be simpler, and we get more complexity going up, turning out not to be simpler. So the Russian doll sense might be the only sense in which complexity increases as we move up scales. And, this illustration from smart biology of what a cell actually is, a neuron in this case, I think makes this point really clearly. So we all carry around in our heads the idea that a cell is kind of like a blob with 10 organelles, a blob of cytoplasm with 10 organelles floating about, but that's just not the case. The microscale is incredibly complicated. And it's not just, it's prokaryotes too are much more complicated than we thought. So biology is replete with rich empirical descriptions of microscale complexity for a wide range of systems, from the molecular to the social. And I think we need to start taking this complexity into account. In another talk, I would tell you about how complexity begets complexity. I'll touch on that a little bit when I get to hourglass emergence.
Jessica, just a small reminder, you have like 3 minutes left or so, 3-4 minutes.
God, only 3 minutes left.
Yeah.
All right. So a natural question is to ask how nature overcomes subjectivity during information processing. And our proposal is that adaptive systems overcome subjectivity by collectively coarse graining and collectively computing solutions to EVA or learning time. And I won't say much about coarse graining since I don't have any time left. I normally would tell you what it actually is because the technical definition matters here, but I'll just say that coarse graining is lossy but true compression. That means it's a simplification, but it doesn't introduce any details that aren't actually present in the system. Okay, Walter, we call this, when the coarse graining is done by the system itself, we call it endogenous coarse graining. Walter Fontana, we developed this idea over many conversations at tea in the kitchen. Walter was part of that. He calls it internal coarse graining. I recommend you check out his paper on molecular coarse graining if you want to understand that. So elements of computation for us are here: input, output, circuit, algorithm, and a notion of correctness, which you can get through a separation of timescales. And as I said before, the slower variables provide the background against which the system tunes. we think about this in terms of circuits. We get the circuits, the causality, to go back to Conrad, and I totally agree with his definition of causality interventionist. I would just add that it's a hierarchical concept. And so, as you get more mechanistic, there's still causality, but you get more specific, closer, more proximal, I'd say. So we use what we call inductive game theory to get causality out of time series data and build circuits like these that describe the microscopic configuration of the system. We then reduce these circuits, we compress these circuits using biologically principled dimension reduction, meaning trying to take into account the system's point of view about how it's processing the information in the circuits. I won't go through this for lack of time, but what we get out of this is the architecture of collective computation that we think applies quite broadly. And just to explain quickly, this schematic is unfolded in time. The W's are the states of the environment. There's an algorithm P that the X's use to coarse grain the states of the environment into their opinions or effective theories for how the world works. There's some circuit or causal graph that describes the interactions among the X's. Then the X's collectively compute, that's an algorithm A, to produce macroscopic variables Y. The Y's then feed back to the X's to change the cost landscape, for example, producing new behavior, the Z's in the X's, or new environmental states. And the B is the algorithm that describes that process. Okay, so there are many ways to, this is just a small point that we can come back to in the discussion. There's many ways to represent how all of this works, and there's no single way to do it. So this is a nice slide from a paper by Peter Stadler and David Krakauer and Sonia, in which they make this point. And I just want to add to it that we need to combine, to do this well, we need to combine probabilistic and computer science deterministic approaches, I think. And we're really nowhere near doing that in a way that's not kind of inelegant and kludgy. We've done it in sort of inelegant ways. Finally, I'll say what we think this happens sometimes in these systems with this collective coarse graining and coarse graining by individuals is what we call information bottlenecks. It's a term also used by Tishby and Bielek and others in a similar way, but they mean it in a specific machine learning sense. This information bottleneck comes from the coarse graining. It allows the system to build effective theories for how the world works. The effective theory might be wrong, but it allows the system to gain hypotheses for what the right behavior is and produces what we call a macroscopic expansion. So under some cases, the coarse graining, the bottleneck, by redirecting or allocating attention to more appropriately, allows for new behavior to emerge. That's the macroscopic expansion. And I've got that sort of here illustrated with this hourglass framework. So just to reiterate, hourglass emergence, endogenous coarse graining creates an information bottleneck, leading in some cases to innovation and this macroscopic expansion. Now, to come back to my earlier points about how far down do we need to go and screening off, I think by understanding this collective computation through this collective computation approach, what the micro-macro relationship actually is, we are in a position to start asking how screened off the macro is from the micro. And what I want to suggest is that to formalize, there's a transition in information flow. So I said there's diversity across biological systems and how screened off they are. So some systems are very screened off, the macro scale is sufficient. Some systems we have to go down to the micro scale to do the prediction and explanation. And I think what this reflects is this information transition. So we go from a case where there's information flow between micro and macro to one where there's very little flow between micro and macro, and it's mostly between macro and macro. And I've got all of that summarized here.
Jessica, you need to wrap up. I'm sorry.
That's all right. So these are my last slides. So I'll just say, statistical evidence for law-like relationships among a set of macroscopic variables. Macroscopic variables need to be fundamental, not nominal. When there's the degree of information flow between micro and macro is small, we have screening off. We need to ask how sensitive, though, the macro is to microscopic perturbations and whether macro-macro prediction is improved with microinfo. And I have a nice example from James O'Dwyer and Mario Mascarello, which I won't go through, but we can in the discussion if you like, to sort of illustrate a proof of principle. So just to end, I'm proposing that these conditions that I've got here on this slide capture the degree to which the macro scale is essentially an effective termination criterion for the microscale, uncertainty minimizing, so the microscale can tune interactions using the macroscale information. All right, I can stop there.
All right, thanks a lot, Jessica. This was a lot of interesting stuff. a very, very dense presentation, a lot in there. So we have one question from the Q&A. The question is, isn't it interesting to understand coarse graining as a spectrum from many, in brackets, smaller scales to many, in brackets, larger scales? This might help get around choosing scales. This would also mean there may be multiple phase transitions. I can read this again if this was too much. Yeah,
I think I got the gist of it. So yes, I, in another talk, and I would make the connection maybe to renormalization group theory in physics. So basically, you can think about renormalization group and coarse graining as the way that the very small connects to the very large. It's kind of a rigorous way of connecting the very small to the very large. And that's kind of the goal here too, but instead of thinking about this from the kind of physics perspective of how you do coarse graining, the idea is to figure out how the biological components are doing the coarse grainings and how those coarse grainings combine to map the micro to macro in that renormalization group sense. So yes, I think that's right. The only real difference is it's not necessarily the case the coarse grainings that physicists would apply, or those doing are looking for optimal coarse grainings would apply to the system are the ones that we want here. We want to figure out how the components are making those estimates and how the estimates are combining, rightly or wrongly, given the information in the environment, to produce the macro scale. So when I said the macro scale is collectively computed, it might not have high mutual information with the environment because of error and information in information processing. However, it also may recover environmental regularities through the collective aspect. That's sort of the 2 points with respect to coarse graining.
Yeah. Thank you. I will maybe ask very quickly a question as well, and maybe you can just very briefly answer it for the sake of time. So I was wondering how figuring out micro to macro relationships is affected by the problems that Konrad has been also talking about. So omitting variables is one problem. Also the impossibility of recovering the underlying causality if the systems are too big. And I guess because we want macro variables to be caused by micro variables, we do deal with problems of causality as well. So how would you see the relation between micro macro relationships and the general problems in causality?
Well, so because of this, it's all made even more complicated by this information processing point I keep making and the error that seems to be inherent in that. Now, back up and say one thing, which is that there is an agreement in biology yet about whether information processing is optimal or not. You will see for some simple systems, it seems to me the information processing is optimal and error is not really a problem. But of course, those systems could have evolved, and solved the problem. Alternatively, they're just simple enough so that error is not really an issue. But there's disagreement about how error-prone biological systems are, and that comes up in economics in another way, which we could talk about in the panel discussion. That's relevant here too. But the micro-macro thing, in order to get the causality in the map, you have to titrate. So you start with a hypothesized correct input based on independent information, and you start with hopefully some statistical regularities at the macro scale that you observe, but you don't know whether they're fundamental yet or just nominal. And then you have to titrate inductively, go back and forth to get the causality and the mechanism, or the more refined. I think a mechanism is just more fine-grained causality, essentially. So even in Pearl's framework, there's there is a hierarchy of causality. And so the question comes back to that screening off question. How much of the fine-grained mechanism is required given your questions, given the scale at which you're working? So, and I think the burden is on us to show first that if we're going to rely at the macro scale for prediction and explanation, that the macro scale is in fact screened off from the micro. Meaning it's not, so it's still caused by the micro, but it's not, the causation is largely at the macro scale. The summary statistics, the coarse grained variables at the macro scale are sufficient.
Okay, yeah, thanks a lot, Jessica. So yeah, we'll see you later on in the panel discussion. Then the last talk before we do have the panel discussion is from Melanie Mitchell. So Melanie, I see you are here.
Yes, I am here.
We also see you now. So I'll give a short intro. Melanie Mitchell is a Davis professor, also at the Santa Fe Institute. Her current research focuses on conceptual abstraction, analogy making, and visual recognition in artificial intelligence systems. She's the author or editor of 6 books and many scholarly papers in the fields of AI research, cognitive science, and complex systems. Okay, so if you are ready, you can just go ahead, and yeah, we do see your screen.
Okay, and you can hear me okay?
That's good. Yes.
Great. Thank you so much for inviting me to this fun meeting. So I'm going to talk about why AI is harder than we think. And the short answer is because we still don't really appreciate how complex intelligence really is. So the history of AI is one of boom and bust cycles. You know, you can see this in this very rough plot of sort of the outlook for AI, how optimistic people were about AI achieving sort of human level intelligence. And there's been at least 2 AI winters, one of which was right as I got my PhD, which was somewhat unfortunate in terms of job search. But right now we seem to be in an unending AI spring in which people are extremely optimistic. So, you know, examples of this optimism back in 2015, the Guardian newspaper predicted that 5 years later, 2020, we'd have self-driving cars, we wouldn't have to drive anymore. 2016, again, 2020 was somehow a common target for predicting self-driving. Elon Musk in 2019 promised that a year from now, again, 2020, we'll have over 1 million cars with full self-driving, et cetera. And then just this year, he said, I would be shocked if we don't achieve full self-driving safer than humans this year. I would be shocked. Well, I don't think any of us would be shocked since we've seen this pattern. And in fact, here's what one AI researcher said about self-driving. Perhaps expectations are too high. This will eventually result in disaster. Suppose 5 years from now, funding collapses as autonomous vehicles fail to roll. Every startup company fails, et cetera, et cetera. This condition is called the AI winter. Now, this was actually said in 1984 by Drew McDermott, an AI researcher. So you can see the kind of cyclical nature of this thing. Back then, expectations for near-term self-driving cars and many other things were quite high. And about 5 years later, everything collapsed pretty much. So will that happen now? I don't know. We're already seeing some signs of disappointment in the self-driving world, but we'll see how this all turns out. But I do want to say that this idea of over-promising and over-optimism in AI goes back a long time. Even someone as brilliant as Claude Shannon in 1961 predicted that we'd soon see something like the robots of science fiction fame emerging from labs. A few years later, Herbert Simon, one of the pioneers of AI and a Nobel Prize winner, predicted that within 20 years of 1965, machines would be capable of doing any work that a man can do. Of course, the sexist language of the 1960s. And Marvin Minsky, founder of the MIT AI Lab, predicted a few years later that within a generation, which is maybe 20, 25 years, the problem of creating AI will be substantially solved. Well, of course, none of these things happened. And many years later, another pioneer of AI, John McCarthy, said, well, the problem was AI was harder than we thought. You know, back in the early days, people thought that it wouldn't be that hard to create human level intelligence. Well, again, we're seeing a lot of predictions due to the deep learning revolution and other progress in AI. Shane Legg, the co-founder of DeepMind, back in 2008 predicted that we'd see human level AI in the mid 2020s. Mark Zuckerberg said in 2015 that one of the goals of the company was to get better than human level at everything, including general cognition, within the next 5 to 10 years. And Rich Sutton, a pioneer of reinforcement learning, just recently estimated a 50% probability of human level AI by 2040. And Stuart Russell, in his most recent book, asked, when will super intelligent AI arrive? It will probably happen in the lifetime of my children. And he noted that this was more conservative than that of the typical AI researcher. So these people who are predicting, human level AI, super general cognition, super intelligent AI, I would venture that these terms are not well understood what they mean, if they mean anything at all. And I wrote a paper a couple years ago called Why AI is Harder Than We Think. I probably should have called it Why AI is Still Harder Than We Think, in reference to John McCarthy. And I think the problem is that we really lack intuitions and understanding about what intelligence is. So in the paper, I talked about 4 fallacies that I thought promoted over-optimism in AI. And I'll talk about those briefly. So the first one is that the fallacy that narrow AI is on a continuum with general AI. So this is the idea that when we make some progress in a narrow area of AI, that's predicting progress on general AI. It's a first step. And you can see these kind of press releases of these various programs being called steps towards creating general intelligence. So Hubert Dreyfus, the philosopher, said a long time ago that this first step fallacy, the claim that since any progress, any improvement in our programs, no matter how trivial, counts as progress on this continuum, he claimed that, in fact, there was a discontinuity in the assumed continuum, and the unexpected obstacle was called the common sense knowledge problem. So I'll talk about that a little bit later. The second fallacy is that easy things are easy and hard things are hard, meaning that things that are easy for humans will also be easy for machines, and vice versa. So for example, a few years ago, the deep learning pioneer, Andrew Ng, said, if a typical person can do a mental task with less than 1 second of thought, we can probably automate it using AI, either now or in the near future. Implying that these easy things, these things that take us less than 1 second of thought, will be easy for machines. A more subtle version of this fallacy was from the original paper on AlphaZero from DeepMind. And they said that Go is among the most challenging domains in terms of human intellect, and implying that, therefore, getting a computer to play Go will be sort of a harbinger of general intelligence, AI. Whereas, in fact, Go is indeed very challenging for humans, but games and other abilities that are much easier for humans, like the example Gary Marcus used of charades, playing charades, are still way beyond the ability of any computer program. We've seen recently with the rise of generative AI, generative language, generative images, that there's been a lot of very optimistic coverage in the press and in among researchers. So, the Washington Post wrote a glowing article about how AI can create any image in seconds, bringing wonder and danger. And New York Times recently wrote an article, an opinion piece, saying we need to talk about how good AI is getting. And these referred to things like OpenAI's GPT-3 program, which indeed can, as everybody here knows, can generate amazingly human-like text and often does very well on reasoning benchmarks, and has been seen as many people as a step towards general intelligence. But it turns out that if, it can write an essay on the causes of the Civil War, the American Civil War, but if you ask it very simple physical reasoning questions, like this one, this is my prompt. I put a green box on top of a blue box. Okay, imagine that. I put a yellow box on the green box and another red box on top of that. I then took off the red box and put it beneath the blue box. What is on top now? Okay, so you probably have a mental image and can answer that what's on the top now is the yellow box. But if you ask GPT-3, it gets it wrong. And if you ask what's on the bottom, well, you could probably take your mental model and imagine that the red box is on the bottom, but it also gets that wrong. So these simple kinds of physical reasoning abilities are lacking. So one of the examples of easy things are hard. These models also have problems with things like negation. If I ask GPT-3, write a sentence that is not about ice cream, it writes, I'm not a fan of ice cream. Or even these generative image models like DALL-E, which can, as the Washington Post claimed, create any image from text. If you ask it the same kind of idea, a yellow box on top of a green box, which is on top of a blue box, it can never generate that. I tried many times, and here's the kinds of things it generates, because it doesn't have this concept of the sort of physical placement, doesn't understand these prepositions. And like if you ask it the negative problem, give me a bowl of fruit with no apples, it's unable to do that either. Every bowl of fruit it produces is rife with apples. So these kinds of things that are easy for humans turn out to be hard for machines. And I don't think anybody's been able to train these systems to do better on these kinds of things that are hard to get examples of in the training set. So this goes back to Moravec's paradox, that it's comparatively easy to make computers exhibit adult performance on things like intelligence tests or playing checkers. This was written actually before computers were beating chess players and Go players. And it's difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. And I'll add common sense. The third fallacy was what I call the lure of wishful mnemonics, a term I got from Drew McDermott paper from 1976 that was about how people in AI would use human language, anthropomorphic human language, to describe what their AI systems could do when the AI systems were actually not able to do those tasks in a human-like way, such as Watson reading all of the healthcare texts in the world, whereas the word read implies understanding. Or Watson understands context and nuance in 7 languages. These terms are something that we're using in this very fluid way, whereas they have a lot of human baggage that comes along with them. Or even saying that AlphaGo has a goal to beat the best human players, not just mimic them. So a computer program doesn't have a goal in the human-like sense. And yet using this language tends to convince us, even researchers themselves, that these machines actually have something that they really don't. And here's a headline recently: Google unveils an AI that's able to create knowledge itself, that learns on its own, using these terms like knowledge and even learns, that are really quite different than what the humans have when they have knowledge or when they learn. So even the names that we give our benchmark data sets, such as a reading comprehension data set, or a general language understanding evaluation, or a cognition level visual understanding. So these are the names that we have given on benchmark data sets to evaluate AI programs. And when they actually outperform humans, as they do on these systems, these benchmarks, how can we blame people from thinking that they have actually achieved general language understanding or visual understanding or reading comprehension? You know, this is the GLUE, general language understanding and evaluation, and its successor super GLUE. And you can see humans right now, this is the human baseline. It's below 6 different deep learning language models. So how can we blame people for assuming that machines are better than humans at general language understanding? Well, it turns out that those are wishful mnemonics, that these systems are able to do well on these benchmarks without the ability that the benchmarks are named after. My final fallacy is the idea that intelligence is all in the brain. So this is the idea that if only we could get the AI to sort of brain scale computing capacity, we'd be able to achieve intelligence. This is this idea of a brain in a vat, achieving intelligence somehow. And you see this in headlines, you know, sort of asking about how AI compares with the computational capacity of the brain, or human brain scale AI, the massive AI chip that has the compute power of a brain, and so on, assuming that if we could only achieve that, we'd then get to AI. And even people in the field, these are 2 prominent AI people on Twitter, saying that all we need to do is scale up these large-scale pre-trained models to achieve general intelligence. Okay. But this ignores a lot of work in cognitive science, which shows that the brain isn't the only thing that's responsible for our intelligence, that our bodies and our interactions with the environment are perhaps equally as important. This is, of course, very controversial, but it's something that people in AI are very slow to take into account. So what are the major open challenges for AI to get to more like human-like intelligence? Well, here's some of them. Things like few-shot learning, generalization, abstraction and analogy, understanding, and this elusive common sense. So let me give you a couple of examples of that in my last few minutes. So it turns out that the most common accident for self-driving cars is that humans rear-end them. You know, what happens is that the car is driving along, human driving behind it, probably too close as humans do, and the self-driving car slams on the brakes unexpectedly, and the human behind it crashes into it. Because the human is expecting the self-driving car to drive like a human, whereas the self-driving car perceives things in the world as obstacles that no human would ever perceive, such as, you know, a floating plastic bag or a tumbleweed. Here in New Mexico, we see things like this. And any human would know that you don't need to stop for this kind of thing, because we understand the physics of the world and how our car will interact with different kinds of objects. We know that birds are likely to fly away, or even, you know, that we shouldn't drive over this pile of glass in the road, or that this snowman in the middle of the road will not run across in front of our car, because we have a vast understanding of how the world works. And this is what you might call common sense. And in fact, this is something that people in AI are pushing hard on. You know, Paul Allen, before he died, started an institute to study common sense in AI. And the US Department of Defense is pouring a lot of money into what they call machine common sense. But it's very difficult. And this is an example that I'll end with. This was an example from a blog post by Andrej Karpathy, he is a deep learning researcher who used to be the head of AI at Tesla. This was when he was still a grad student. He wrote this blog post about computer vision and AI and how far away we are, using this fantastic example of what understanding that we would need to make sense of this image. So yes, what would it take for a computer to understand this image? And there's just a vast amount of things that we know about intuitive physics, about human, what makes something funny, why people stand on scales, how a scale works, what kind of room this is, a locker room, that this image over here in the mirror isn't another person. And it just goes on. And we know that this is like a joke situation. We're able to abstract and so on. It's a great blog post. I recommend it for reading it. It's still really quite relevant. So I'll say, in spite of enormous progress in specific areas, AI systems are still far from having anything like these general human abilities. And I think this is something that a lot of people in the field don't appreciate. And it's what makes AI still harder than we think. So you probably know that, the first meeting of AI was in 1956 at Dartmouth, organized by these luminaries. And they had some amazing goals, like during the summer, they would figure out how to make machines use language, form abstractions and concepts, solve problems reserved for humans, and improve themselves. I would say this is the most still open problem. But interestingly, Eric Horvitz, who's now the head of Microsoft Research, said back in 2015 that one might even say that this proposal, if properly reformatted, could be resubmitted to the NSF today and would probably get some funding by some excited program managers. So indeed, a lot of problems in AI are still quite open. And I think that people are being over-optimistic about how soon we're going to get to anything like human-level AI. Thank you for listening. I talk a lot more about this in my recent book on AI. Happy to answer any questions.
Yeah, thanks a lot, Melanie. There are a few questions in the Q&A. The first I'll ask is, does AI need an artificial, in brackets, artificial body to evolve from weak to strong?
Sorry, does AI need an artificial body to evolve from weak to strong? Oh, I see, weak to strong AI. Exactly. Okay.
Yeah, and whether it needs an artificial a body, and whether it could be an artificial one, but some kind of body. That's the question.
Yeah, I think that's a great question. And, nobody knows the answer because, first of all, we don't know how to define sort of strong or general AI. I think that nobody agrees on what the definitions are. And we also don't know how embodied we need to be. So today, an embodied AI means like an agent working in a virtual environment online, and like in a computer game. People would call that embodied, but of course that's not having a real body. So do we need to build robots that actually interact with the world? I think no one really knows, and that's very much an open, controversial question.
Yeah. Okay, the next question is, most AI research at university these days happens in deep learning, that is pattern recognition or misting. This is very remote from McCarthy's characterization of AI. Isn't the rebranding of machine learning as AI perhaps the most fundamental fallacy?
Yeah, I mean, it's a funny history because machine learning initially was opposed to AI. AI was defined as symbolic approaches, not neural nets. And you can see this explicitly in the writings of the early AI folks. So machine learning was explicitly, different conferences, different journals, different approaches, relying much more on statistics, and then suddenly machine learning equals AI. So I don't know how this evolved, probably due to economic forces. and the sort of commercialization of a lot of AI technologies. Now there's a lot of talk about how deep learning has limitations that only can be overcome by integrating it with more symbolic approaches, but nobody's really come up with very effective ways to do that. So, these different camps of AI have been going on forever, and it's hard to say what's maybe something completely new is really needed.
Okay, another question is, do you have any insights to share on what the different factors are that lead to such an interest in creating an AI with quote unquote general human abilities? What are the incentives involved and the major risks as you see them?
Right. So why create human-like AI? Why not just create unhuman-like AI that can do things that we have problems with? And that's something we've done, of course, already. We've created AI systems that can navigate for us in our cars, that can transcribe our speech, that can figure out how to predict protein structure and all kinds of things. Very much harder for humans. So I think that there's domains in which we really don't want the AI to think like us. We want it to think differently, like in perhaps scientific applications, where it can understand patterns and it can come up with patterns and data that are things that we would never have thought of. But in human domains in which the AI is interacting with us, like in driving, for example, we do want it to think like us. We do want it to have the same kind of common sense that we have, or else the systems will be unpredictable, and this is going to be a big problem. And we've already seen that happen. So I'll just say that, there are certain domains in which we probably need machines with common sense like humans, and other domains where we don't.
Okay, I will ask also a question from one of the organizers, Tomek Korbak. So his question is, how far could plain scaling of existing AI techniques, for instance, unlabeled data, transformers, lead us? Can we automate the majority of intellectual labor using language models?
That's the billion-dollar question. $1 billion, I don't know. This is something that companies like OpenAI are putting all their bets on scaling. And we see that these systems get better and better in some sense with scaling, meaning increasing the size of the networks, increasing the scale of the data. But one problem is that the benchmarks that we use to assess this progress often have problems in that they allow for shortcuts, meaning that if you ask, you say, okay, this is a reading comprehension benchmark, I'm going to test my language model on it. Language model does great, except it doesn't do it in the way I wanted it to do it. It uses like statistical correlations in the data that are not reflective of comprehension in the sense that we want it to be. So whether that kind of approach can, if you have more and more data, actually match humans in every sense, I don't know. I think that's still an open question. I would bet against that, but I've been wrong before.
Yeah. Okay, so I may also ask a final question before we have a short break and go into the panel discussion. So you've been saying right at the beginning that we have a limited understanding of the nature and the complexity of intelligence, which is why AI is harder than we think. And I would ask you, with the knowledge that you have at that point, what would be your best working definition of intelligence? You've been naming a few things, but maybe you could elaborate on this a bit more. And also, how would you would you reason about that in the first place? I'm now thinking about Gael's talk, for instance, or also Konrad's, which have been a lot about complexity that we may not be able to understand in any intuitive way. So yeah, but what's there to do if the only thing we have is our intuitions and the phenomenology of our cognition? So how would we reason about the ingredients of intelligence? Yeah, and the possibility that it's actually too complex for us to grasp.
All in the next 30 seconds, right?
Exactly. Yeah. Okay. Yeah. I see. It's a big question.
Yeah, it is a big question. So
we can also move that to the panel discussion.
I think that would be a great question to move to the panel, and I'd love to hear everybody's thoughts on that. I think there's many kinds of intelligence, and the word, perhaps thinking of it as something, as a thing that we have to explain, perhaps is misleading us, since it might not be a single thing.
All right. Okay. Yeah, I guess then everything else in the panel discussion. Yeah, again, thanks a lot for your talk. We're gonna have a 10-minute break and then yeah, start with the panel discussion with Konrad, Jessica, Melanie, and Gael. So yeah, see everyone then in 10 minutes. All right. Hello, everyone. Back to our symposium on computational approaches to the mind. We're going to have the panel discussion now with Konrad Cording, Gael Verrocourt, Melanie Mitchell, and Jessica Flack. Those panelists have already been introduced when they gave their talk, so I won't do this again, but I'll quickly touch upon what we've been hearing about today. So today's talks have been on a variety of things. Konrad has been talking about causality. Romain made us aware of assumptions inherent in Eurocomputationalism. Gael emphasized external validity and predictive models. Joe talked about information flow and also the importance of developing tools for scientific progress. And Melanie told us about problems and common assumptions in AI research. So this is quite some material, which we will also touch upon in the discussion. The main goal of the discussion is to talk about the really most fundamental challenges in scientifically understanding the mind or processes of the mind using computational approaches, and how to overcome those, or if we can't overcome those, how to at least respond to those or handle them. We will go into some of the theoretical, epistemological, and methodological issues that have been raised by the speakers. We'll also have questions around technology and tools, scientific practice, and future roadmap kind of questions. We also have questions from the audience, which I will pose sometime in the second half of the discussion. So the audience is encouraged to ask questions. Again, make sure that the question has not already been asked, and upvote questions that you like. Okay, so I would like to start with a very big picture question, which I think in one way or the other might already touch upon what we've been hearing today in the talks, and I think everyone can say something about it. So my question is, how can we build less theories that can grow quite big without a tie to empirical grounds, or where we may have a great deal of uncertainty and the ideas developed and sustained? So I'm thinking here about studying the mind. So when we do that, studying the mind, that we might tend to build too much theory on loose, false or absent empirical or epistemological facts. And it is hard for false theories to die out. So I think this is a particular problem. So my question is, what's your stance on this? Do you agree, disagree? How would you make the ties between our ideas and the real world stronger? So it's a very epistemological question I'm asking here. So one thing I think about here could be, for instance, having a more frequent cycle of theory, experiments, and building tools. Or also, we might need to focus on theories that give less fuzzy predictions. So theories whose predictions map unequivocally onto something measurable in the real world. So yeah, how would you make the ties between ideas and the real world stronger? That's the very broad general question. And everyone is encouraged to say something on that.
I mean, I'd love to say something about it, but I will make a sociological, not an epistemic point here, which is, I think both neuroscience and cognitive science have maneuvered themselves into a corner, and now they're stuck between a rock and a hard place, which is, we have that expectation that you do an experiment, present some data, and tell us how the mind works at a very deep and very meaningful level. And that's, of course, impossible. Therefore, if you want the data that you have is beautified by a lot of like wonderful ideas, and it all therefore doesn't hang together. And as long as we're so addicted to this cycle of people doing that, and as long as we make the promotion of young scientists be dependent on that, they have no choice. So I don't think we don't know how we should approach it. I think it's just that we don't, because the system that we built doesn't allow us to do so.
if I can piggyback on what Corinne said, with which I completely agree. I think one of the challenges that I've noticed personally, especially talking to young scientists, to grad students, people like this, is that the older scientist has expectations that don't really match what's possible. And one of the reasons I think is because of the history of science, because the kind of questions that people were tackling many years ago and the kind of answers that were expected are now either trivial or not accepted anymore. And especially, I think, one of the really challenging problems is that I've worked a lot with psychologists. I really find psychology interesting as a science, but the psychologists that are now senior PIs were trained in qualitative research, and certainly not in most of them, and not in quantitative research.
Can I add something?
Yeah, sure. Go ahead.
So, of course, there's the desire to make our theories valid and to ground them in empirical reality, and that's worthwhile, obviously. But in one way you can do that, or one way we sort of advocate doing that, is to adopt a kind of comparative model systems approach, where you have a variety of model systems from different scales or that seem to be quite different but are representative in some way, and then you derive principles from studying them together. But I think the deeper point I was trying to make in my talk is that we have to be empirically grounded to do theory for most biological and social systems in which there's a lot of information processing, precisely because they're error prone, and these systems are building their own effective theories for how the world works. And in order to make progress, we have to understand what those effective theories are. So my talk is about the utility of an inductive approach to building theories. And pretty much all the work we do combines an inductive approach with, and I mean, I'm a pluralist, so I also see the role of, toy models and so forth that aren't empirically grounded. But there's been a huge problem of doing phenomenological modeling where the variables, the parameters and so forth in our model are not grounded in reality. And the reason for that, I'm suggesting, is precisely because of the information processing. We haven't taken that seriously enough. So I don't think the way forward is what you're suggesting, but for this reason, not just so that we're on firmer ground from a kind of intellectual point.
Could you maybe clarify what you mean here by information processing? That's the crucial, that's the key thing that you are considering here. But I'm not sure I actually understand the point that you're making.
Yeah, sure. So I'm very operational in all of my concepts and definitions. Information for me is uncertainty reduction, so it's very Shannon-tied. Information processing is the taking perceived regularities in the environment and as input and then producing some kind of aggregate or collective level output. And that process is almost identical to computation. So information processing and computation are basically how you turn perceived regularities in the environment into work.
But that shifts that's then a question of how would we know what the perceived regularities are?
How do you know? So that's one thing. For example, so when we do inductive game theory, which I didn't have any time to explain today, the idea is to use, I'll give you a concrete example in a second, but to use independent information to circumscribe a space of strategies that the components or organism might be using, and then to look in, say, time series data for evidence of those strategies. And ideally, the strategies bear some principled relationship to each other, so there's a kind of mapping between them. That's another point. And then you find evidence for the strategies in the time series You discard the ones for which there's no evidence, they're probabilistic. You can think of them as causal relationships, and then use those strategies to build circuits describing the microscopic configuration of the system. This is already coarse-grained because the strategies are a coarse-grained representation of how the component or organism perceives the world, right? And then you build circuits that sort of describe the microscopic configuration of the system. You do dimensionality reduction on the circuits that's biologically principled. Now, this is all super hard, what I'm saying. I'm just giving you kind of the workbook. That's biologically principled, meaning that you take into account what you know about the kinds of algorithms the system could be using in order to aggregate the strategies or opinions of the components to produce a collective output. So, I mean, there's so many problems in here, like how you compare different algorithms, what defines hardness, lots of typical complexity science problems. So I'm sweeping tons under the carpet. But the idea is to, and when I say extract regularities from the environment, obviously there's a huge area, many areas in neuroscience and cognitive science that are specifically about this. And so the work is there. People are trying to figure out what organisms understand about the world, right? I'm just saying that we need to do that not just at the individual level, but also when we're building circuits at any level. What are the components perceiving? What are they estimating? How does that inform their strategic or behavioral relationships? How are those things combined to produce a collective output? All of this can be done inductively. But with theory, like the theory part is the dimension reduction is still there. It's just that you're doing it with the system's point of view in mind. You're asking what constraints there are on computing in the system, on the types of algorithms that could be used, and you're restricting your consideration to those instead of applying ones that you think might get you the optimal answer. That's not the perspective. And in the end, it might be the same. And for some systems, it probably is the ones that are more optimally processing information.
Maybe just one last follow-up question here for you. So if we think about processes of the mind, either instantiated in the brain or in machines, how would you apply what you've been just describing to those kind of systems? So you talk about perception of different of individual components of a system. So when thinking about the brain or an AI system, how would this work there?
So for example, sparse coding, is a technique that was really originally applied in neuroscience by David Field and others. And you can use that at multiple levels. The idea of sparse coding is to figure out what are the regularities, to use the sparse coding approach to figure out what the regularities are that the system is using to make decisions. So that's one example. But there are plenty. I mean, it's just the same. It's just doing the same kind of. You're still doing dimensionality reduction, but you're just asking, given what you know about how a neuron processes information or what a neuron's computational capacity is, given all the highly detailed information we have about a neuron, how could it be interpreting inputs, right? And we've been doing this now. I mean, now we know that a neuron is incredibly complicated, right? And there's still that question of how much of that complexity is relevant, right? So that's all part of this. But I think for a long time, we were assuming a neuron was quite simple, actually. Even neuroscientists were assuming that. And so, how does that inform that more nuanced understanding inform our spike timing, for example?
Okay. It's interesting. Very different answer to what Gael and Konrad have been touching upon. Melanie, do you also want to say something on the initial question?
No, I don't really have anything to add to what everybody else is saying, so I'll wait for the next question.
All right. So I'd like to go into a few questions on artificial intelligence, and complementary to that also in neuroscience. So one question concerns interpretability. So in AI, we can look into the system and fully observe it. So that's different from the brain, but we may not have in any intuitive way on understanding of how it solves a given task. That is what the higher level mechanism is, so to speak, by means of which it can do a task well. So this is known as the interpretability problem. And we've been, some of you have been also talking about this explicitly today. So do you think, and also some of you have been partially answering this question, I think, do you think that the quest of understanding AI is misleading, and we might simply need to accept that it is beyond an intuitive understanding? Or do you think there are ways forward to tackle it? Related to this, how could solving or working on the problem of interpretability also affect studying the mind in the brain?
So I'd like to piggyback on part of your question, maybe not all of it, but you mentioned the notion of intuition. Intuition, as far as I'm concerned, I believe is learned. It's not born with intuition. Learn intuitive physics, they fail in the beginning, it hurts. When I worked a lot on quantum physics, I had intuition about quantum physics. So if you're saying, can we intuition about some AI system? Well, if we play a lot with it, yes. Or if it matches the intuition we already have, if it matches our intuitive physics, if it matches, so I don't think there's something intrinsic in intuition. Just a side comment.
I do feel like there are ways we can understand a lot of these large scale AI systems, but it's finding the right kind of conceptual variables to do it. It's analogous to what people have done in dynamical systems theory, where you have to find the right, reduction in dimensionality, as Jessica was talking about. You have to find the right sort of phase space, if you will, for making sense of this. And this is something that a lot of people are working on these days and have brought a lot of insights into how these things are working, but it's a very difficult problem. And, I think the same thing applies to the brain at a much higher, more complex level, since they're not only is the brain much more complex and the components much more complex, but there's all the interaction with body and environment and social interaction and so on. So, however, I'm optimistic that we will make maybe at least some progress in this science.
Yeah, and I would just add to what Melanie's saying. We have this. First of all, I think that the understanding is, like Melanie said, phase space maybe can be mapping between architecture and output. There's a lot of different possibilities. And it may be that the language that we have for understanding is a mathematical or physics language that doesn't mean something to a lot of people. It means you have to have a background. You have to know what a phase space is in order for it to be meaningful. And that's just the way it's going to be. I think that's something that we have to accept, and it's going to apply to the brain and as well as to, neural nets and machine learning, AI, and so forth. And the second point I want to make is what counts for as explanation and prediction. And I think a lot of times we carry with us a sort of quite traditional physics view, where it's sort of like law-like regularities derived from an understanding of initial conditions, and it's kind of deterministic, and we can do prediction. And I think this might be wrong, and that in a lot of complex systems that we're interested in, what we really are going to, what we're going to be able to sort of predict is not the outcome of a trajectory, but certain kinds of organizational principles that maybe aren't, they're not quantitative in the sense of the physics sense of making a prediction to so many decimal points, right? These are like logical organizational principles that make sense, or that you would expect to see in systems given the challenges that they are encountering. Conflict management is a very general one. Certain kinds of robustness principles or others that you can predict these things, but it's not going to be like in the traditional physics sense. And by the way, this idea. There, David Deutsch and what's his collaborator's name? She's slipping, her name is slipping my mind at the moment, but they have this constructor theory idea, which is sort of what they're thinking is like a meta theory for physics. It's very controversial, but they're making a very similar point that what really maybe we need are sort of these logical information processing principles. And I think that's a very different way of thinking, but it's something I think we should start taking seriously.
Conrad, you were about to say something?
Yeah, exactly. I want to contrast it a little bit with the negative, like I hope that putting the negative view clearly on the table helps us thinking about it. So if I want to do machine learning on, say, face recognition, and I can look at the principal components of faces. Now, it's just one way of dividing it into units of explanation. I'm not saying those are the ideal units of explanations, but there's some. The first few principal components will show that there's a face. It's like low frequency, all very smooth. And the reason why it's low frequency is principal components of natural scenes are basically Fourier components. So the first few of them will tell you a lot about the face. What's the average brightness of the face? Is your face bright at the top versus the bottom? And if I have to answer questions with that, indeed, the first few principal components explain a lot, and I can build a decoder relatively well on the first of them. But if I now take them away, I can recognize you perfectly fine after throwing away the first 100 components of your face. It's all still there. If all the lines that show me where your face is and what and all the properties of your face, they're still totally there. So it's possible that there's a recoding that makes this go away, but in such a scenario, we might be in that situation where, sure, we can give an explanation how it works. It's just the wrong explanation how it works. It turns out that if you want, instead of having a few components that we base our decision on, we use, and there's good reasons for machine learning why we'd want to do that. We instead use all 1 million dimensions that an image has, and some of them very much, and then other components less and less and less and less and less. But it never ends. And if we cut anywhere, there's still all that information that happens later. So in that sense, yes, I can explain how we recognize a face. It's just that my explanation is fundamentally wrong. And so that's why I kind of at least want to put the theory out that there will never be an acceptable description of things like how you recognize that that's my face.
Yeah, go ahead.
If I may, as always, when we get in those discussions about understanding, interpreting, explaining, but there are different goals, and the different goals come with different answers. There's and we've seen somewhat a bit some of the gradient in the current discussion. There is the goal maybe of explaining one specific set of learner, for instance, the face detector, and that goal may be very important for societal reasons. Cynthia Dwart makes very well the point that we're not going to put in production. Well, we are putting in production automated decisions, and they might be all kind of automated decisions. They don't have to be neural nets, and we would like to be able to guarantee that they're not doing too much harm. And if we have an idea of where to look for the harm, which means we have some intuitive understanding of the thing, then we can find this. And so that's kind of teasing apart a specific decision function. It doesn't even have to be a neural net. And then at the other end of the spectrum, there's understanding the dynamics of learning of the neural net, which is something which is probably useful for neural network research or AI research, and there will be never a final answer, but it's to me the process is the same process than in physics, where we are going to try to perturb the system, try to play with it, try to reduce it in certain directions, guided by theory or pure empirical results. And then do we know whether our understanding is a good one or a bad one? Well, it's a good one if it allows us to extrapolate behavior of the neural net, of the AI, and design either better AI or test better AIs or things like this. There's no final understanding, of course.
Yeah, it's the common saying, all models are wrong and some are useful, right? That's neuroscience and AI as well.
Those of us here in the sort of in the United States and the West in general like to focus on specific individual biased explanations. We like simple causality, but most of the systems we're talking on are talking about are extremely collective, right? And so we need to get our heads around collective causality, synergistic effects, for example, and how to talk about and think about those, because those are going to be our explanations. I think just from a colloquial standpoint, everyday life, most of us are not comfortable thinking about the fact that the cause is in the network, the cause is in the circuit, the cause is not in any single component. I mean, maybe there's a few components that contribute disproportionately, and so you can say in those cases that the dominant cause comes from a node or so forth, but most of the time it's going to be more distributed, and we need better language for talking about that and just become more comfortable with it.
And we also need the humility to admit how far our definitions reach there, and I don't think as a field we have that yet. There is the idea that as machine learning people should hand over an understanding of how exactly things work, and I think we there's certain things that we just can't deliver.
Yeah, I think so. While most people would also agree that all models are wrong, you should use the ones that are useful, but also ones that are, according to Occam's razor, the simpler ones. But it sounds like all of you kind of disagree with that. So simplicity does not bring us forward here. I feel that's kind of the vibe that I do get. I want to comment on that.
Of course, Occam's razor is crucial for statistical and epistemic reasons, but the problem is we're in what we could call complex systems or messy word, and Occam's razor actually works well for internal validity. If you take physics, Occam's razor works well for somewhat of a pure experiment that's done in a lab. But in real life, a feather and a big piece of lead don't fall at the same speed, at the same velocity, because the friction doesn't mean that the basic law of Newtonian gravity are wrong. So I think those systems, those AI systems, and the brain that we're studying, they're both messy systems. They're not pure systems.
Yeah, maybe it's good at that point to get back specifically to what I've been asking Melanie, the big question at the end. So on the nature of intelligence and the complexity of intelligence. So if it's all very, very complex, how would you then go about intelligence? What would be your working definition? How would you advance AI research in thinking more about what intelligence is? And others, of course, they can comment on that as well. But
the term intelligence is very fuzzy. It encompasses a lot of different things, and it may not be the right term to be using. And in fact, I think at the very beginning of the field, there was a debate about what to call this. And AI wasn't necessarily the first choice, but I know that Herbert Simon was pushing for complex information processing, which may be a better term because it's a little bit more broad and maybe quantifiable. So I think there's many different kinds of intelligence, and we humans are an example of one kind that's particularly adapted to our particular environment and our incredibly social kind of processing that we do. We're a very social species, and that's very different from other intelligences. So I think maybe we should just get away from the whole term altogether and come up with some better terms that are more scientific.
And sorry, but I'm still wondering, what is then? Can you, if you do have ideas at the point, what AI is missing for it to be generally intelligent?
Well, I talked about, I gave kind of a list at the end of my talk, which
exactly
involved a number of things, and especially things like abstraction and generalization, which is something that we humans are able to do quite well, at least in a lot of contexts, not in all, but and that AI systems are very bad at. So that's, but that's one capacity. There's other capacities that we humans have that AI systems don't have, that are maybe particularly useful in our environment, but maybe aren't needed in for other kinds of environments or tasks. So I think you have to be very, more specific about what kind of intelligence is needed.
What the problem is.
You wanted to say something, Jessica?
No, I was just reiterating, I was just saying another way what Melanie was saying, which is be much more operational about the problems that you're solving, or you want the system to solve, instead of arguing about intelligence. And the kind of funny thing here is that David Krakauer, my collaborator, and Walter, who I mentioned in my talk, talking about computational intelligence for a very long time. And Walter has inspired a lot of my work, his early work on trying to understand how biological systems compute. And he has moved away from using the term computation because he was sort of like in battle with computer scientists about, the theory of computation and being very like Church-Turing oriented, and moved toward intelligence. So now he speaks of cellular intelligence. And David and I always have battles about this kind of thing. And David's fine with the computational framework, but he tends in his own work to speak about intelligence all the way down. So everyone's in for different reasons, having trouble with these terms. And in the end, it just, like Melanie says, it comes down to being, I think, much more operational. And like I recently had a conversation with someone who, and you see this on Twitter all the time, who keeps saying that general intelligence is about the Turing test. And I just find this to be like, really? I mean, we don't even agree really what the Turing test is. And it's just so generic, like we need to be much more specific. And the actual work people are doing is much more specific, but it's not well synthesized or integrated yet.
Yeah. I'm thinking here about, then in turn, I'm thinking here about the problems we have in operationalizing concepts. So kind of the argument that Talia Coney makes in I think the paper was for generalizability crisis. So the problem that we take a concept like intelligence and then we operationalize it via some task, but it might be a wrong operationalization. So we do have problematic mappings here. And we might be wrong about what the task, what important tasks are in the first place. So the concepts we are trying to operationalize. Do you have any comments on that?
Are you asking everybody?
Yes, yeah, it's directed to everyone, yeah.
I mean, I think Tal is referring to intelligence as a human trait that is used in psychology, including, well, based from personality psychology, but is also interesting in all related aspects. It's clearly an ill-defined notion, and there won't be. I don't believe there'll ever be a pure definition of it, and so it's a very composite notion. But there's this idea that there is something that varies between individual, and it might vary across multiple dimensions, but that relates to their ability to evolve in the world in complex situations, and so relates to has an impact on their socioeconomic status, and is also caused by their socioeconomic status. So I mean, I don't really think that Tal is putting a word that is like a sort of fundamental AI, general AI, strong AI, a notion behind this.
Oh yeah, so I was I think he didn't put this, at least not in the paper, into the context of AI. So I've been now asking this in the context of AI. Yeah.
Well, I think that's one of the problems with the term intelligence, is it can mean many very different things, like what it's talking about, which is differences along some cognitive dimension versus differences, between machines and humans as a species. And, when you talk to people about AI and you say, well, AI doesn't have common sense, and people say, well, a lot of people don't have that either. It's using the word in quite different ways, right? So it's another problem with these anthropomorphic terms. And I think that's, a problem with intelligence too.
I must say, for exactly that reason, I try to avoid talking about intelligence and instead talk on learning, because learning is still hard enough to define, but at least it's more narrow, and you can get relatively far with a change a system now to do better in the future. That feels like it gets at what learning is about. But intelligence, it's like be good at using information from the past to be good in the future. But then we have like good and better. There's two goods that are now in it, and they're both poorly defined.
Yeah. Okay. I'd like to ask a more nuanced but still general question that's often asked, I guess. But it's interesting to see how this question is being asked all the time. So what do you think is the role, now getting back to more to the brain, what is the role and the merits of deep learning? What will the role and merits converge to as an analysis or modeling tool in neuroscience? How would you comment on that?
So wait, is the question, what is the role of the merit of deep learning as applied to neuroscience?
Yeah, so as an analysis and modeling tool, because that's being done a lot. So yeah, as a tool to gain knowledge in neuroscience, either in neuroscience or cognitive neuroscience. Yeah.
But hold on, let's distinguish the two uses. There is deep learning as a tool that I don't think anyone can ever disagree with. I have tissue samples. I want to detect how many cells are in there. I use deep learning for that. There's a lot of cases where deep learning is part of a toolkit that we use. And then there's cases where we use it more as a model of that.
I'm talking about the latter, yeah.
Oh, okay. Cool.
Yeah, go ahead.
Well, so the first something that's really important to stress is deep learning is a tool. It's a technology. It's there today, like whatever, Python, C, you name it. It's not. There's nothing, magic behind this. And then second, I mean, why do I find it very valuable for like empirical studies in neuroscience? Because today it's maybe the thing that works best to model natural-ish stimuli. And so that allows us to move towards studying the brain, the living brain, in more ecological situations. And before, when we study the brain in more ecological situations, you need basically to manually annotate the situation, which is incredibly reductionist. You're boiling down the situation to just a small set of things. Whereas if you use tools that readily model the natural situation, you get a much richer way of analyzing the brain. And don't get me wrong, I mean, we could have done this with wavelets before CNNs. It's just that CNNs capture a high level of abstractions, which wavelets don't. But there's nothing wrong doing it with wavelets, and we can very well study, the primary visual cortex with wavelets. It's just a tool that describes the natural statistics of the data as I'm concerned.
Yeah, this that's, well, it's on both the features. So well, on the data side and the model size, it is very high dimensional. I guess that's also what you've been pointing to in your talk, right? That you you can have very high dimensional models and use a lot of input features as well.
I'm convinced we shouldn't be afraid of high dimensionality. The problem with high dimensionality is it makes explaining, understanding, you name it, harder, because I can't fit in a sentence about how something works. I can't apply this to 10,000 different descriptors. But I believe reality is high dimension.
Sorry, what did you just say?
I believe reality is high dimension.
Oh, strong claim, strong claim.
A very, very strong claim. So I wanted to just defend a little bit why I think deep learning thinking is so useful when modeling neuroscience, but probably a lot of other things as well. So in machine learning, if you're really malicious, there's only one concept that ever stood the test of time, which is machine learning works if we have systems where we can make changes and we do the changes that are helpful and we don't do the changes that are not helpful. And by doing that enough, we get good. You can argue at some margins, but in reality, almost everything boils down to it. Gradient descent is just a way of finding out in which direction in weight space things get better versus worse, and we do the good ones, we don't do the bad ones. Now, given the parsimony of this principle that is really in everything, in anything that even human societies and companies do, you can say kind of, if there's anything that we expect to happen in brains, it would be that thing, which is that the good changes happen, the bad changes don't happen. Now, how exactly the brain figures out what are the good changes and what are the bad changes, that's maybe a little more complicated. But it's a very parsimonious, simple way of thinking about the goals and mechanisms of learning.
Yeah, I was just about to. Yeah, sorry. Go ahead.
It's kind of funny. I mean, there are papers on gradient descent basically being isomorphic to evolutionary dynamics. David has written some and others. So it's the same in neuroscience. We're getting the same question again that we had forever in evolutionary biology, which is about sorting algorithms essentially. And it's not, and I'm an evolutionary biologist. And I moved for a long time. I've moved away from that. I'm much more interested in the computation and construction process than the sorting process. And so it's the output of deep learning models, that's interesting, not the deep learning really itself. We actually already have frameworks to understand what that is.
But the brain must use some mechanism to figure out which synapses it changes and how. So I don't understand why you declare that as not being interesting per se.
Because it's been the problem of evolutionary theory forever. And so it's not that it's not a problem, but it's been like the dominant question. It's just, if you take my point that gradient descent and evolutionary dynamics in certain cases can be shown to be more or less isomorphic, we have a long history of doing that. And so this is part of my work too, to be fair, Conrad, right? So in our work, there are two parts to collective computation. There's, working out the coarse grainings and how the algorithms that aggregate the coarse grainings to produce some output. And then there's the output, the mutual information of the output to the environment. The mutual information is just a generalization of evolutionary dynamics. So and we think of this in terms of termination criterion, like how the organism or the system knows that the mutual information is high with the environment. That's adaptation, okay? And so gradient descent, this mutual information framework, evolutionary dynamics, they're all in the sort of same space. And what's interesting work there are the people, really mathematical people who are showing that they're isomorphic. I think that's interesting, but it's just dominated evolutionary theory for so long. Whereas the parts of evolutionary theory that have been lacking are much more like in the developmental space. And, there have been developmental biologists working forever, and there's Evo-Devo, but those trajectories were separate for a long time. They've converged. It started converging really in the 90s, I would say. And now we're sort of adding to that convergence, taking seriously collective effects. And so I think the problem is much more in the production of multiple overlapping timescales, where time and space scales come from, how these things get computed. And then the older question is, how do we know that what's good, essentially? Right? But it's the older question.
But I want to just make sure that our audience understands where the difference between you and me come from. Now, like you come from evolution, and indeed, it's a meme. It's evolution makes things better. Yeah, every little kid like hears about that. But if you talk with neuroscientists and you look at the models that they have about how plasticity unfolds, their models don't have that flavor at all. And in fact, if you say like, hey, we should assume that the brain kind of does gradient descent, they're like, what, you're crazy. Like, show me where that even is in the brain. Like I think these two fields think extremely differently. And same thing with cognitive scientists. I don't, I think it's wonderful that you come from evolution, but I don't think that that's at all where our field is at the moment.
Here's another way of putting it, Conrad. So I totally agree with you that neuroscientists, and in fact, the collective behavior literature is similar in some sense, that not collective intelligence, but collective behavior literature has been interested in pattern formation, but not really in the fit of the pattern to the environment. Right, that part's missing, but they're super rigorous and they've got the tools to do it. They just haven't been focusing on it. I mean, I come from collective behavior evolution, and in neuroscience, I agree. I take your point, but what I'm saying is that the work to understand evolutionary dynamics, gradient descent, mutual information, these new information theoretic frameworks for generalizing all of this, predictive coding, all of this is in the same space. The work is there. It's a matter for neuroscientists, yes, to start taking it seriously, to use it, but the work is already there. They don't really have to invent this stuff. They can borrow it and borrow the advances that are being made, or in understanding, like I said, the isomorphisms, borrow those more general frameworks to unite this, like Carl Friston, predictive coding, our information theoretic approaches. It's all going to be unified, but the work is there. Where the work is still very much in development is in the kind of process that produces the hierarchy. That's where we lack general principles and mathematical formalisms that can potentially be used in a variety of different spaces.
But hold on, let me push a little bit back on the work is there. So I think there's a big difference. So if I look at an ecosystem, you can say locally, maybe for the role of an animal in its niche, we can define gradient-like things. But the brain is special, which is, if you want, all the cells are not malicious. They're all trying to help the same cause in a way, which means that there is, as opposed to the system, if you want, like the need and desire to kind of produce a system which is like, hey, someone should have told me that thing. Can you like make sure next time you like there is like a positive, how can we provide one another with the useful information that is shaping the context within brains? And I don't see it so much outside of neuroscience in evolution. And enlighten us maybe about like where you see kind of this like deep information propagation for gradient descent thing in evolution.
We'd say a little bit more about that, because I think there's a piece here that's sort of that I'm missing in this discussion.
So when we talk about brains, we often talk about the brain consists of many different steps that happen in sequence to produce an output, which is behavior, along with the credit assignment problem, which is kind of where in this very long hierarchy did stuff go right or wrong that ultimately made you like do the right or the wrong thing. This need to, if you want, assign credit where it's due is kind of solved by arguably, and I know this is an oversimplification, but it's arguably solved by trial and error across generations in evolution. I know that the genotype-phenotype mapping does some important things out there, and Artem Katznachev, for example, is doing some cool modeling there. But by and large, like those systems are very different. At least that's how it feels to me.
Okay, so there's a lot in there. So a couple of things. Like one is I don't want to argue about the stakes. I'm not prepared to do it, but I'm definitely not convinced that for two reasons that neurons are all cooperating. Two, even if they are cooperating, they still have essentially conflicts of interest that come from error and having different windows on the world, and sort of their interests are not totally aligned just from that alone. So, but all of that's dealt with in evolutionary dynamics, right? So that continuum from competition to cooperation is part of evolutionary dynamics modeling, right? But then you raise the question of credit assignment. And what I hear in the credit assignment, like there's a sequence of things that has to happen. It's like what I'm talking about in terms of computation / development. But where in there do you assign the credit in terms of getting regular output. And I see that as a levels of selection / target of selection problem. Again, an old debate in evolutionary biology, still not yet resolved, but comes back to, this question that I raised in my talk about how far down do we need to go and how do we know? And so there is an open issue in there. And the open issue is, and I think it's an information theoretic issue. I mean, not just, I think it can be formalized information theoretically. I don't think the explanation is necessarily information theoretic, but that's how far down do we need to go? Is there like a mesoscale level explanation? Do we have to go to the microscale? Can we reside entirely at the macro, like John would argue for motor control, right? And how do we know? And I think that comes down to measuring the information flow. I think we're making headway, quantifying the information flow between the micro and macro. And if the information flow is low, then we can reside at the micro and testing different partitionings of the system. So maybe you're measuring information flow between micro and macro, or increasingly coarse-grained micro and macro, right? To very coarse-grained. So that's sort of one way to get at it. And it relates to this work that David and Nihat and I and some others did on individuality, where we formalized information theoretically the idea of what an individual is as temporal, and essentially as temporal uncertainty reduction. And the reason we did this is we wanted to get away from the mistake we feel has been made and still being made in evolutionary biology of stating we know what the entities are a priori based on things that we think are proxies, like a cell membrane. So it's your question of how do we assign credit? What do we know what the right level or entity is? And we're suggesting that you can do this information theoretically. You can pull out these temporally cohesive things. And maybe we want to put space back in there. We want to get away from space because it privileges certain things over others, like cells and human bodies over social systems, but not necessarily in a good way. So just to sort of summarize the discussion so far, I think that the fit to the environment, that's whether it's predictive coding, mutual information, traditional evolutionary dynamics approaches, all of that we're getting work on that's showing these things are isomorphic, and we'll eventually, not very far off, have a general framework for dealing with that. That work is there, like I keep saying. Where it's not is in the computation of these things, like you're saying, and in the understanding of how the sequence develops. Where there's still an opening that sort of bridges the two is in the credit assignment / unit of selection thing. Like, how do we know robustly what a unit is, or in a principled way what a unit or genuine causal entity is?
I want to, at that point, I'm not so I think it's a lot. I'm not sure I could follow all of your, Jessica's and Conrad's discussion. It's quite quick, but I want to touch upon information theory, because you've been mentioning it now a few times as well. And you, Jessica, you use information theory in your work, and Joseph Lizzie as well. I want to generally ask what the use and limits is of information theoretic methods, because those are, I mean, as a means of finding out which variables are the important ones, or as you said, Jessica, at which scale is the decisive one in micro to macro relationships. So there are limits in information theory as a statistical tool. So what's your general comment on that from everyone who wants to say something about that?
I just start by saying that I'm not an information theorist. So I work with exceptionally good information theorists like Nihat I, right? So, the real deal. So with that caveat, I would say a couple of things. Information theory is, it's not about dynamics. So it's, we use it to formalize things, and to sort of get at the dynamics, but you still need, other approaches. It's not like the solution. Another is that, there are continuous and discrete issues, technical issues in there you have to be careful about. A lot of times when we're using our information theory formalisms, we need, complete probability distributions, which you don't always have. Now, there are versions of softer versions of it that don't make those demands. So there's all sorts of technical issues to be aware of. But I think the main one is the dynamics point. So information theory isn't, it's not dynamical. And so it's not going to tell you really, it might help you. It helps us in our work, like give a formal definition of what an individual or an entity is. but it doesn't tell us how the entity arises. It doesn't have anything to say about that. For that, we need this computational or developmental framework, right? So it's useful in unifying mathematical formalisms relating to fitness, to fit to the environment, but it's not going to solve where does the sequence come from? It's not going to tell us which algorithm the system is using to aggregate information. It's not going to answer any of those questions.
Okay. Does anyone else want to comment on information theory in general?
On the statistical point of view, where I want to stress that my understanding of the definition of statistics as opposed to probabilities is trying to start from the data rather than starting from the model. And as you know, in my experience as a statistician, is that information theory is useful for to establish theoretical results, but it is, like, in a strong sense, seldom directly useful directly in the data, because it's basically useful in the asymptotic regimes where you have a huge amount of data, and there's a very simple IDs, so they just keep coming up in people just thinking that if they apply information theory to the data, they'll have fantastic things, whatever, variable selection with mutual information, things like this. It makes very beautiful paper that seldom survive the test of time.
I mean, just to add to that, there's information theory as a tool, and then there's information theory as a deep connection to concepts, in physics. And I think as a tool, all of those objections that were just raised I got at a little of them myself, are totally important to be aware of. And as I said, there's like softer versions, like KL divergence and so forth, softer versions of mutual information that you can use when you don't have complete probability distributions or whatever. And if you really want, and like a good tutorial on information theory and in physics and the different kinds of entropies, for example, I recommend you look at the Twitter account and website of John Carlos Baez. He just had up on Twitter for the last couple of weeks a great tutorial on different kinds of entropies. Really comprehensible. So, and then there's all sorts of, Simon Dedeo has a good tutorial on information theory too.
Yeah, I've just seen Melanie has been posting in the chat a workshop at NeurIPS on information theoretic principles and cognitive systems. So I guess everyone interested can have a look at that. Okay, so we're almost at the end. It's crazy how time flies. I want to ask one question from my side at the end, and then two questions from the audience. A general question from me is on technology and tools. I'd be interested to hear what tools would help you in your research if they were built or improved. So one could think of software, open source software, new AI technologies that produce new discoveries that we wouldn't be able to produce, or just not much faster. And we do have examples from molecular biology, for instance, on that. Yeah, so what do you think would be useful or even game-changing next generation tools? If you could wish for something, yeah.
So I can give my own little answer
to
that. I believe that a lot of the interesting progress in neuroscience, at least, always comes from new tools. And I believe we will have tools that allow us to, at least in smaller model systems, to get all the information that we possibly want from small systems. And with that, we might be able to basically build digital artifacts that are good stand-ins for actual brains. So what tools does Conrad want? He just wants better, cooler, bigger neurotech, and it applied to simple model systems.
Okay, what would the others say? What would help you in your research? In terms of tools or technology?
I guess I need two things. I'm a very trivial person. I need to be able to put data in my models more easily. And anybody who's worked with real data knows it's really hard because you have to message them. That's the first thing. The second thing I need is I simply need more and better data. That's not a tool, but that's the real problem. That's relates to what Conrad says, but I work a lot on traces of human beings, and there, some of the problems are related to privacy.
Okay. Jessica, do you have a comment? I mean, you do mostly theoretical work, but you collaborate a lot with other people as well. So maybe you can still say something on that.
The funny thing is I started out as very empirical. So I collected tons of highly resolved time series data, and I did like one of the first knockout experiments on the social system, but that was a long time ago. And I'd say like not a lot of my work now is in building these synthetic theoretical frameworks, but it's not so much a tool that I want as more as like an approach. I would love to see more science in machine learning and artificial intelligence where, experiments are being designed to, and I see some of this increasingly, to in a kind of principled way, look at different input data sets, different architectures and so forth, like different combinations of these things, to start getting a better idea or start building a taxonomy that relates, right, the different parts of these systems to their outputs. So it's not so much a tool as a more kind of standardized scientific approach that would allow me to get my head around, like, the settings in which recurrent neural network works as opposed to concurrent one and so forth.
Okay, let's get to one or two questions at the end from the audience. So someone is asking, I would like to ask each participant to briefly reflect on why they do the specific work they do, and more generally, what values do you think are important to consider for practitioners?
I mean, I would be happy to go fast. For me to do brain science, my main consideration is that it's only really possible in domains where we have reasons to believe in a certain amount of simplicity. And that's why I'm very much interested in how the brain solves the credit assignment problem, because it's one of these areas where I hope that there may be some simplicity.
Quickly, these days, what I worry most about is how can we get a better society? It does sound.
Sorry, can you repeat, Gael? I didn't get it.
How can we get a better society? It's as simple as that. And I used to think that AI had a strong role to play there. Now, these days, I'm a bit more worried about these things. And I wanted to say earlier that I'm actually personally not interested in the notion of intelligence, because I don't know whether it's going to help us build a better society or not.
Do you want to say something, Jessica, on that question as well?
I'm sorry, I was typing a response in the chat. What was the question again?
Oh, so the question was, just wait a second. I can't find it. All right, I do have it. Why the work? Why? So, the question is whether you could briefly reflect on why you do what you do, the specific work you do, and what values you think are important to consider for practitioners.
Why? So, okay, so I'm not sure I understand the question, but I'll try to answer the way I see it. So, like, why? I mean, my deep interest is in the kind of origins of biological space and time, and so, I do this work to understand that, where biological space and time comes from. In terms of practical applications or applications for practitioners, I think the biggest one with respect to the talk today is in thinking about how collective your system is and how screened off the scale at which you're working is from the lower level, how we can ask that question in a formally in quite a deep way, but also in a practical way. So I imagine that the sort of we're talking about, my group is talking about, for developing a measure of information flow between the scales that will tell us how screened off macros and micro. I imagine it's going to have a lot of these information theory problems that we've been discussing. And one question is how to then make it useful for, or as a measurement tool. So just to make this a little clearer, in the information theory of individuality work we published, that work, we developed a formalism for thinking about individuality, but we didn't develop the algorithm for applying it to data. We left that for someone else to do. So we have a mathematical formalism based on very few assumptions, really. Almost, I think it's just basically one first principles kind of formalism that I think helps us think much harder about what an individual is and these accredited assignment questions, but it doesn't allow, we can't take that formalism and apply it to data. So to do that, we need like some super smart, coder computer scientists to make an algorithm that will take the formalism and convert it into something that'll be useful on data sets. So thinking about always keeping that distinction in mind, I think is one message. Another is that we need to be aware, we need to be aware of the importance of such formalisms. I think that just the point I made that there's possibly quite a bit of diversity across biology and how screened off the macro scale is. And so a lot of this argument that we're having about this might be due to our own biases, right? And so the burden is really on all of us to make sure we understand that our variables are fundamental and not nominal, even if we're not in the business of deriving them. I've thought about that as practitioners.
Okay, yeah, we're over our time, so we're gonna finish at that point. Yeah, so I want to thank everyone on behalf of the organizing team. So today's speakers and panelists, also the Leverhulme Doctoral Scheme for sponsoring the event. So thank you a lot for your talks and the debates that we just had. It's been an absolutely great day with quite some food for thought, I think. And of course, a big thank you to the audience as well. So we will put the recordings on the event website, also the speaker slides, and there will be also, there is also the YouTube channel to watch or rewatch everything at a later time point. So yeah, thank you again for the talks and the debate, and goodbye to everyone, and take care.